Ever stop and think about how the devices you use every single day actually work? I mean, you hold your phone, use your laptop, maybe even flip a light switch. And yet, the science behind these things is mind-boggling. What if I told you all of this, every piece of tech, every solid object around you, works based on one deep, hidden layer of physics that's both simple and crazy complex at the same time? Here's the twist. You don't need a PhD to understand it. You don't even need to sit through long lectures or memorize equations. All you need to do is sit back, relax, and let me walk you through the weird, wonderful world of solid-state physics. Trust me, it's not as dry or boring as it sounds. We're talking about the very stuff that makes up the gadgets in your hand, the materials that run your world, all happening at the atomic level. And just wait. By the end of this, you'll start looking at your phone, your TV, or even a simple piece of metal in a completely new way. This is where science meets everyday life in the most unexpected ways, and I promise you'll be blown away by what you'll learn. But before that, drop a quick comment and let us know where you're watching from and what time it is for you. It's amazing how we're all connected, each of us chasing that perfect night's sleep. If this resonates with you, like this video, subscribe to our channel Restwise and join the journey. We're more than just a sleep channel. We're a community of sleep explorers, discovering how a great night's sleep can truly transform your life. Now, get comfy and let the wonders of solid-state physics guide you into a peaceful sleep. Introduction to solid-state physics. Let's start at the very beginning, solid-state physics. You might be wondering, what exactly is solid-state physics, and why should I care? Well, imagine this. You're holding your smartphone, or maybe you're typing on your laptop, and everything seems to work so effortlessly. But if you really think about it, all these devices, all this technology, relies on something pretty incredible happening at the atomic level. Solid-state physics is the field of science that helps us understand how matter behaves in its solid form, particularly how the atoms inside materials are arranged and interact. This, in turn, explains how materials conduct electricity, absorb light, and even how they hold their shape or break down. At its core, solid-state physics is the study of matter in its solid state. It might sound a bit abstract, but stay with me. What's fascinating is that everything you see, touch, or use is composed of atoms and molecules, and how they interact with one another determines the properties of that material. Whether you're holding a piece of metal, glass, or even rubber, it's all about how the atoms are packed together, how they move, and how they affect one another. Now, think about this for a second. Have you ever wondered why some materials, like metals, are excellent conductors of electricity, while others, like rubber, are poor conductors? Or why diamonds are incredibly hard, while other solids like graphite, another form of carbon, are soft? The answer to these questions lies in the atomic structure of the materials, and understanding that structure is what solid-state physics is all about. So, let's break it down a little more. Solid-state physics looks at how the atoms in materials are arranged. Atoms don't just sit there randomly. They have a very specific, ordered arrangement, especially in crystalline solids, which makes these materials different from amorphous solids like glass. Crystalline solids, like the salt you sprinkle on your food, have a repeating pattern of atoms, forming a crystal lattice. This repeating structure is what gives crystalline solids their strength and stability, and it's why these materials tend to behave predictably under different conditions. On the flip side, amorphous solids, like the glass of your phone screen, have a more random arrangement of atoms. This lack of order in the atomic structure gives amorphous solids different properties, like how glass can break more easily compared to something like a crystal. So, in essence, The way atoms are arranged in solid materials directly impacts how those materials behave in the real world. But that's just the beginning. The beauty of solid-state physics lies in its vast applications. When scientists understood how atoms in solids behave, they were able to create materials that have radically changed our world. Think about semiconductors. Without the understanding of solid-state physics, we wouldn't have the microchips that power your computers, smartphones, or even smartwatches. The invention of semiconductors came from deep knowledge of how electrons behave in solids, and it's one of the most important breakthroughs of the 20th century. You see, the movement of electrons within materials is at the heart of so much technology today. By understanding how electrons move, how they gain energy, and how they interact with atoms, scientists can design materials with specific properties, like the ability to conduct electricity or insulate against it, absorb light, or even bend and flex in unique ways. And the reason solid-state physics is so important is that it bridges the gap between the microscopic world of atoms and the macroscopic world we interact with every day. It explains why the material in your smartphone screen is glass, why your laptop has a metal body, and why certain components are made of specific metals or plastic. It's not random. It's all based on the science of solid-state physics. But it's not just about making gadgets and tech. The principles of solid-state physics have also led to innovations in other fields, like medicine. Take the MRI, for example. MRI machines rely on the behavior of certain materials in magnetic fields, and understanding this is rooted in solid-state physics. Superconductivity, another concept we'll dive into later, has potential applications in everything from high-speed trains to energy-efficient power grids. Solid-state physics is also a key player in the development of new materials. Researchers are constantly discovering ways to manipulate atoms in materials to make them stronger, lighter, or more efficient. This might sound like something out of a science fiction movie, but it's happening right now. Think about nanotechnology. Tiny materials, smaller than the width of a human hair, are being engineered to create more efficient solar panels, better batteries, and even new medical treatments. The discoveries we make in solid-state physics don't just improve technology, they reshape entire industries and open up new possibilities for the future. So, as we go on this journey together, you'll begin to see just how fundamental solid-state physics is to the world around you. It's the backbone of nearly all modern technology, whether we're talking about electronics, energy, or even the future of artificial intelligence. Solid-state physics is at the center of it all. And the best part, you don't need to be a physicist to understand it. Just a curious mind ready to explore the wonders of the material world we live in. By the end of this session, you'll have a clearer picture of how solid-state physics not only explains the behavior of everyday materials, but also drives the innovations that define our modern world. So, get comfortable, relax, and let's start peeling back the layers of this amazing field. You're about to dive into a world where the tiniest particles create the biggest changes. And trust me, it's going to be a fascinating ride. Classification of solids: crystalline and amorphous. Now that we've laid the groundwork for what solid physics is all about, let's zoom in on one of the most fundamental distinctions in this field, the classification of solids. Not all solids are created equal. In fact, one of the first things you'll learn in solid physics is that solids come in two major types: crystalline solids and amorphous solids. This isn't just a textbook distinction either. It's something that affects everything from how materials are used in tech to how they behave under pressure, heat, or light. Let's start with crystalline solids. These are probably what most people picture when they hear the word solid. Think salt, quartz, or even the metal in a smartphone body. What makes crystalline solids unique is that the atoms inside them are arranged in a very precise, repeating pattern. You can think of it like a 3D grid where each atom has its place, and that pattern continues over long distances throughout the material. This arrangement is called a crystal lattice, and it's incredibly important in determining how the solid behaves. Because of this highly ordered structure, crystalline solids are typically stable, strong, and have very defined physical properties. For example, they melt at specific temperatures, and their strength and conductivity can often be predicted based on the way their atoms are arranged. A great example of this is diamond. It's made entirely of carbon atoms, just like graphite in a pencil, but in diamond, those atoms are locked into a tight, three-dimensional crystal lattice. That's what makes diamonds incredibly hard, literally one of the hardest materials known to man. On the other hand, something like table salt, sodium chloride also forms crystals, but with a cubic arrangement of sodium and chloride ions. That's why salt often has a naturally cubic shape when it forms crystals. You're literally seeing the atomic structure on a macro scale. Now let's flip to the other side of the spectrums, amorphous solids. These materials are solids too, but their atomic arrangement is much less organized. Instead of forming a neat, repeating pattern, the atoms in an amorphous solid are jumbled together, like a random pile of bricks rather than a neatly built wall. A common example you see every day is glass. If you've ever dropped a glass cup and watched it shatter, you've seen amorphous behavior in action. There's no internal order to distribute the stress evenly, so when one part breaks, it just keeps going. The lack of structure in amorphous solids gives them very different properties from crystalline ones. For instance, while crystalline solids have sharp, defined melting points, amorphous solids soften over a range of temperatures. If you heat up crystalline salt, it'll suddenly transition from solid to liquid at a specific temperature. But if you heat glass, it doesn't melt so much as it starts to slowly soften and bend. There's no single point where it changes state. This is due to the lack of long-range order in the atomic arrangement. Rubber is another good example of an amorphous solid. It's flexible, stretchy, and doesn't break easily under pressure. But that also means it's not as structurally stable as something like a crystalline metal. That's why we use rubber for things like tires or bands, where we need flexibility and shock absorption, not rigidity or sharp precision. To make things even clearer, let's lay out the key differences. Crystalline solids have a long-range, repeating atomic structure. Amorphous solids don't. Crystalline solids melt sharply at a specific temperature. Amorphous solids gradually soften. Crystalline materials are usually more rigid and mechanically strong, while amorphous materials can be flexible or brittle, depending on how they're made. And when it comes to examples, think diamonds, salt, and quartz for crystalline. Think glass, rubber, and plastic for amorphous. You might be wondering, why does this even matter? Well, the classification affects everything from how materials are manufactured to how they're used in real life. Take your smartphone, for instance. The screen is made from a type of amorphous glass that's chemically strengthened so it doesn't shatter easily, but the chips inside, the semiconductors, are made from crystalline silicon. Why? Because crystalline materials offer the consistent, predictable electrical properties needed to build tiny, powerful circuits. If the silicon weren't crystalline, the electrons wouldn't move through it in a controlled way, and the device simply wouldn't function. Even in more advanced applications like solar panels, this classification matters. Amorphous silicon is cheaper and easier to produce, but less efficient. Crystalline silicon is more expensive but offers better energy conversion. Engineers have to choose which one to use based on the product's purpose, cost, and performance requirements. So, whether we're building electronics, designing new materials, or just trying to understand the world around us. This basic classification into crystalline and amorphous solids is essential. It's not just a technical detail. It's a lens through which we can understand why materials behave the way they do. And once you start to notice these differences, you'll see them everywhere, from the glass windows in your home to the materials used in airplanes' batteries, and even biomedical devices. Understanding how atoms arrange themselves in a solid is like understanding the blueprint of a building. If the foundation is organized and structured, the building is strong and predictable. If it's a little chaotic, you get something more flexible, but also more prone to surprises. And that, right there, is one of the most important takeaways in solid physics. Structure defines behavior. Whether you're holding a crystal or a chunk of glass, now you know. What's happening inside is what really shapes everything on the outside. Crystal lattices and Bravais lattice types. So far, we've talked about how solids can be crystalline or amorphous, right? Now it's time to zoom into the world of crystalline solids a little more closely, literally, because at the heart of any crystalline solid is something called a crystal lattice. If you've ever wondered how atoms are actually arranged inside a crystal, this is where the magic happens. Let's break it down. A crystal lattice is basically the 3D blueprint of how atoms, ions, or molecules are stacked in a crystal. Think of it like the scaffolding of a building, but instead of beams and bricks, it's made up of repeating units of atoms. This repeating arrangement is super important because it's what gives crystals their distinct shapes and properties. For example, the reason salt crystals form cubes and snowflakes have six-sided symmetry. That's all thanks to how the atoms are arranged in their respective crystal lattices. Now, to simplify this entire idea, scientists use something called a lattice point. A lattice point represents the position of an atom or a group of atoms. If you connect these lattice points across space, you get the lattice structure. And here's where it gets even cooler. Despite the endless variety of crystals in nature, they can all be classified into just 7 basic crystal systems. And when we consider all the ways those systems can be arranged in 3D space, we get exactly 14 unique Bravais lattices. Yup, just 14. That's it. Every crystalline solid in the world can be built from one of these 14 arrangements. It's kind of wild. Let's break it down. The 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral, also called trigonal. Each of these systems is based on different combinations of edge lengths and angles. For example, the cubic system has all sides equal and all angles at 90 degrees, while the triclinic system has all sides and angles different. These crystal systems act like families. And within each family, we can have different lattice types depending on how the atoms are positioned within the unit cell. That's where the Bravais lattices come in. So, what's a Bravais lattice? It's basically a unique way to arrange points in 3D space such that every point has an identical environment. Auguste Bravais, the French physicist who figured this all out in the 1800s, realized there are only 14 such arrangements that satisfy this condition. These 14 are derived by combining the 7 crystal systems with different types of centering primitive P, body-centered EI, face-centered ZF, and base-centered to C or AB. Let's take an example to make this super clear. The cubic system. It gives rise to 3 of the 14 Bravais lattices. Simple cubic, S-seed, where atoms are located only at the corners of the cube. Body-centered cubic, BCC, where atoms are at the corners and one atom sits in the center of the cube. Face-centered cubic, CFCC, where atoms are at the corners and at the center of each face of the cube. These tiny changes in atomic arrangement make a massive difference in how materials behave. For instance, iron at room temperature has a body-centered cubic structure, which makes it hard and relatively brittle. But when heated above a certain temperature, it switches to face-centered cubic, becoming more malleable. That's why steel can be shaped when it's hot. It literally has a different atomic structure. Or take aluminum. It has a face-centered cubic structure at room temperature, which is why it's both strong and highly ductile. That internal arrangement gives it the ability to bend and stretch without snapping. All of this is due to how the atoms are arranged inside the material. Just a different Bravais lattice, and you've got a completely different set of properties. Even diamonds owe their incredible hardness to their underlying lattice. While they don't fall into the basic Bravais list, because of the basis of multiple atoms per point, their underlying structure is still built on a face-centered cubic lattice with a very specific atomic basis. The strong covalent bonds and perfect 3D network of carbon atoms give diamond its world-famous toughness. Now, here's where this gets really useful by knowing the Bravais lattice of a material. Scientists and engineers can predict how it will behave under different conditions, whether it'll conduct electricity well, if it'll expand under heat, or how it might fracture under stress. It's kind of like having the DNA of the material. You know exactly what it's made to do. Let's recap quickly. A crystal lattice is the 3D repeating pattern of atoms in a crystal. These arrangements fall into one of 7 crystal systems, and when we consider all the ways atoms can be centered in those systems, we get the 14 Bravais lattices. These 14 are the building blocks for all crystalline materials. Everything, from the strength of steel to the sparkle of a diamond, comes down to one of these patterns. That's what makes them such a big deal in solid physics. And honestly, it's kind of amazing when you think about it. You could be holding a quartz crystal, or a chunk of copper, or a piece of snow. And even though they all look and feel different, deep down they're all just repeating arrangements of atoms. That's the power of symmetry in structure. It's simple, it's elegant, and it shows you how organized nature really is when you zoom in close enough. Unit cells and crystal parameters. Now that we've got a good grip on crystal lattices and the Bravais types, let's zoom in a little further. To the level of a single repeating block in a crystal. This is what we call the unit cell, and it might be small, but it's absolutely crucial. Think of it as the smallest chunk of a crystal that, when stacked over and over in space, builds up the entire solid. It's like the base tile in a massive mosaic. Repeat it in every direction and you've got the full picture. So, what exactly is a unit cell? It's the smallest unit of a crystal structure that shows the full symmetry and layout of the entire lattice. When you repeat this unit cell in all directions, you reconstruct the whole crystal. That's the basic idea. If you've ever seen a pile of sugar cubes, that's a great visual. Each cube is like a unit cell. Stack them side by side, row by row, and soon you have a block of sugar. Same idea, just at the atomic level. Now every unit cell is defined by a set of measurements known as crystal parameters. These parameters tell us everything about the shape and size of the cell. There are 6 of them, 3 edge lengths labeled as a B and C. These represent the lengths of the unit cell edges along the 3 axes, Y and Z. 3 interaxial angles called alpha, beta, and gamma. These are the angles between the edges. So alpha is the angle between B and C, beta is between A and C, and gamma is between A and B. Based on how these parameters vary, we get the 7 crystal systems. For example, in a cubic system, all the edges are equal. So A equals B equals C, and all the angles are 90 degrees. That's a perfect cube. But in something like a monoclinic system, all 3 edges have different lengths, and 2 of the angles are 90 degrees, while the third is not. That slight twist in the structure changes everything. To give you an idea of how this translates into the real world, materials that form in cubic systems, like salt or copper, tend to have a very symmetric and stable structure. But monoclinic or triclinic systems, with less symmetry, often show more complex behaviors under stress or temperature changes. Now, there are different types of unit cells depending on how atoms are positioned inside the cell. The three most common are simple or primitive unit cell. Atoms are located only at the corners of the cell. Body, centered unit cell. One additional atom is placed in the very center of the cube, along with the corner atoms. Face, centered unit cell. Atoms are placed at each corner and also at the center of each face of the cube. Even though these changes sound small, they drastically affect the material's properties. Take iron, for example. At room temperature, it has a body-centered cubic structure, making it strong and relatively rigid. But when you heat it up, it shifts into a face-centered cubic structure, which makes it more ductile and easier to shape. So, blacksmiths heating metal to work with it. That's literally solid physics in action. Let's talk about coordination number for a second. This is just the number of nearest neighbors an atom has in a structure. In a face-centered cubic unit cell, each atom touches 12 others. In a body-centered cubic, it's 8. The higher the coordination number, the more tightly packed the atoms are, which usually means higher density and better strength. That's why metals with a face-centered cubic structure, like aluminum and copper, are both strong and malleable. There's also something called the atomic packing factor, often shortened to APF, which tells us how much space inside the unit cell is actually filled with atoms. It's a percentage. For example, simple cubic has an APF of about 52%. That means almost half the space is empty. Body-centered cubic improves on that with around 68%. Face-centered cubic is the most efficient, at around 74% packed. This matters because more densely packed structures usually conduct heat and electricity better and have higher strength-to-weight ratios. That's why understanding unit cells is essential in designing everything from skyscrapers to microchips. Speaking of microchips, silicon, the base of all modern electronics, crystallizes in a structure called the diamond cubic lattice, which is a variation of the face-centered cubic. In this structure, each atom is bonded to 4 others in a very specific pattern. This allows silicon to behave as a semiconductor, which means it can sometimes conduct electricity and sometimes not. Exactly what we want for controlling digital signals in devices. Another cool thing, the volume of the unit cell can help calculate the density of a solid. If you know the mass of the atoms in the cell and the cell's volume, you can get the material's density with just a simple division. It's another great example of how something microscopic directly connects to something measurable on a human scale. So let's recap. A unit cell is the smallest repeating unit in a crystal lattice. It's defined by 6 crystal parameters, 3 edge lengths A, B, C, and 3 angles S, alpha, beta, gamma. The way atoms are arranged in this cell, simple, body-centered, or face-centered, determines the material's structure, density, strength, conductivity, and a lot more. Every property you can touch, bend, break, or heat in a solid traces back to the shape and contents of its unit cell. That's the real beauty of solid physics. It takes something as abstract as atomic arrangement and shows you how it builds the world around us, one repeating block at a time. Miller indices and crystal planes. All right, now that we've got a good sense of unit cells and how crystals are built up from tiny repeating blocks, let's get a little more precise. Imagine zooming into a crystal and wanting to talk about the orientation of a particular slice or layer inside it. You'd need a way to label and describe that layer so someone else can understand exactly what you're looking at. That's where Miller indices come into play. Miller indices are a simple yet powerful way to describe the orientation of planes in a crystal. These planes are essentially flat surfaces that pass through points in the crystal lattice, and understanding them is critical in everything from X-ray diffraction experiments to figuring out how a crystal will cleave when it's cut. Now, let's build this up from the basics. First, let's define a crystal plane. A crystal plane is a flat, two-dimensional surface that cuts through a crystal lattice. These planes can run parallel to certain axes or intersect them, and they're key to understanding a crystal's symmetry, growth patterns, and even how it breaks or reflects light. To systematically identify and label these planes, we use Miller indices, a set of three integers written in parentheses like L10011 or OR1. These three numbers tell us how the plane intersects the three axes of the crystal lattice, the x-axis, y-axis, and z-axis, which correspond to the A, B, and C unit cell lengths, respectively. Here's how it works. Step 1. Find the intercepts of the plane with the A, B, and C axes, measured in terms of the unit cell dimensions. For example, maybe a plane crosses the x-axis at 1 unit length, the y-axis at 2 units, and the z-axis at infinity, meaning it's parallel to the z-axis. Step 2. Take the reciprocals of these intercepts. So for our example, we'd get 1, 1/2, and 0. Step 3. Clear the fractions by multiplying all the values by the least common multiple to get whole numbers. In this case, we'd multiply by 2, resulting in the Miller indices Li2, 1 yor. Simple, right? What's brilliant about this system is that it doesn't matter where in the crystal you start. What matters is the orientation. Planes with the same Miller indices are parallel and evenly spaced throughout the lattice. Let's take a practical example. In a simple cubic structure, plane cuts only the x-axis at 1 unit and runs parallel to both the y and z-axis. The I11 Yoa plane cuts the x and y axis but is parallel to the z-axis. And the I111 plane, it intersects all three axes at 1 unit each. It's the diagonal slice, and it turns out to be quite important in materials like diamond and silicon. Why are Miller indices useful? First, they help visualize the internal geometry of a crystal. For example, engineers working on semiconductors need to know exactly which planes to etch or grow material on, because different planes have different atomic arrangements and energy states. The OS10ARV and I111 planes in silicon, for instance, have totally different surface energies, which affects how they react during fabrication. They're also critical in X-ray diffraction studies, which we'll talk about more in the next section. When X-rays bounce off atomic planes inside a crystal, they create patterns that scientists can use to determine the structure of the material. Each set of planes reflects X-rays at a specific angle based on its spacing and orientation, and Miller indices are how we categorize those planes. Another fascinating application is in mechanical properties. Crystals don't always break randomly. They tend to cleave along certain planes. For example, in sodium chloride, common table salt, cleavage happens most easily along the LS1R0 planes. These planes are more widely spaced and have fewer bonds across them, so they require less force to separate. Now, here's something cool. Not only can you label a single plane using Miller indices, but you can also describe a family of equivalent planes using curly brackets. For instance, AV10 represents all planes that are equivalent to I10 by symmetry, like L10 and their 0 in a cubic crystal. Similarly, square brackets like A1 represent directions rather than planes. Let's talk spacing for a moment, because this comes up a lot in diffraction and thermal conductivity. The interplanar spacing, or distance between two adjacent parallel planes with the same Miller indices, is inversely related to the square root of the sum of the squares of those indices. So, the LS2R0's plane is closer packed than the I10's plane. And when you get into X-ray diffraction formulas like Bragg's law, this spacing becomes critically important. Bragg's law is a core concept that connects Miller indices, interplanar spacing, and the angle at which X-rays reflect from a crystal. The equation is usually written as n times lambda equals 2d sine theta, where n is an integer, lambda is the wavelength of the X-ray, d is the spacing between planes, and theta is the angle of incidence. This is where things get really satisfying. You use the Miller indices to find the plane, calculate the spacing d, measure the diffraction angle theta, and boom, you can back-calculate the structure of the entire crystal. So to wrap up, Miller indices are a compact way to describe crystal planes and directions. They're incredibly useful in both theoretical and practical solid physics. Whether you're analyzing how a crystal will reflect X-rays, break under stress, or behave in a microchip. And all of this is made possible through a simple process of taking intercepts, reciprocals, and simplifying. In the next section, we're diving straight into the magic of X-ray diffraction, where these planes we've just labeled start lighting up and revealing the secrets of atomic structure. X-ray diffraction and structure determination. And now that we've got a solid understanding of crystal planes and how we label them using Miller indices, it's time to unlock one of the coolest tools in all of solid physics, X-ray diffraction. This is where science gets almost magical. We're talking about a technique that allows us to literally see the arrangement of atoms inside a crystal without ever having to cut it open or even touch it. And the way it works, all thanks to waves symmetry and some beautiful geometry. So, what is X-ray diffraction? Let's start with the basics. X-rays are a type of electromagnetic radiation, just like visible light, but with much shorter wavelengths. Typically on the order of 1 angstrom. That's about the same size as the spacing between atoms in a solid, which makes X-rays the perfect probe for exploring crystal structures. When you shine X-rays onto a crystal, something fascinating happens. The rays don't just pass through, they interact with the tightly packed planes of atoms inside the material. These atomic planes act like mirrors for the X-rays, causing them to reflect and interfere with each other. And if the conditions are just right, these reflected X-rays combine in a way that creates a diffraction pattern, a specific set of bright spots or rings that contain the fingerprints of the crystal's structure. This phenomenon is described by something called Bragg's law, which is at the heart of X-ray diffraction. It's written as n times lambda equals 2d sine theta, where n is an integer representing the order of the diffraction, lambda is the wavelength of the X-ray, d is the distance between atomic planes, the interplanar spacing, and theta is the angle between the incident X-ray and the crystal plane. Here's how it works. When the X-rays strike parallel planes of atoms, some of the rays reflect off the top layer while others penetrate deeper and reflect off lower planes. If the path difference between these reflected rays is exactly equal to a whole number multiple of the wavelength, like 1 lambda, 2 lambda, and so on, then the waves constructively interfere and you get a strong signal at that angle. If not, they cancel each other out. By measuring the angles and intensities of these diffracted beams, scientists can work backwards to figure out the spacing between planes, aka the d value, and ultimately reconstruct the 3D arrangement of atoms in the crystal. It's a bit like solving a puzzle. You're given the shadows, and you have to figure out what object cast them. Let's take a real-world example: salt or sodium chloride. When X-rays are passed through a salt crystal, they produce a distinctive square pattern of bright spots on a detector. This pattern directly reflects the cubic arrangement of sodium and chloride ions in the crystal. In fact, the earliest X-ray diffraction studies on salt in the early 1900s were what first proved that matter is made of repeating atomic structures. Solid physics literally started here. And then there's the case of DNA. One of the most famous X-ray diffraction images in history is Photo 51, taken by Rosalind Franklin in 1952. That single image, just a series of X-shaped smears, contained enough information for Watson and Crick to determine the double helix structure of DNA. So yes, X-ray diffraction isn't just about metals or semiconductors. It has shaped biology, chemistry, and even medicine. In solid physics, X-ray diffraction is also used to distinguish between different crystal structures. Say you've got two samples of the same element, like carbon, but you're not sure whether they're in a diamond structure or a graphite structure. Shine some X-rays on each, and you'll see completely different diffraction patterns. That's because diamond has a three-dimensional tetrahedral lattice, while graphite has flat, hexagonal planes. X-ray diffraction sees that difference instantly. Another powerful tool is the powder diffraction method, where instead of using a single crystal, you use a fine powder made up of tiny crystallites in random orientations. When X-rays hit this powder, they diffract in all directions, creating a ring pattern on the detector. The position and intensity of these rings can be analyzed to determine the phase, symmetry, and lattice constants of the material. It's widely used in materials science, metallurgy, and quality control for manufacturing. Now, let's talk structure determination. Once you've collected your diffraction data, you can use mathematical techniques like Fourier transforms to turn that data into a model of the electron density within the crystal. That's a fancy way of saying you can map out where all the electrons, and thus the atoms, are located. The more detailed the diffraction pattern, the more accurate your model. Software plays a big role here. Programs like Crys Tailsilos are used to build and refine atomic models based on the experimental data. These models are not just academic. They're essential in designing new materials, improving pharmaceuticals, and understanding defects that might weaken a material or change its properties. Oh, and here's something wild: scientists have now combined X-ray diffraction with free electron lasers, creating what's called femtosecond crystallography. This lets them capture snapshots of crystals in motion, literally watching chemical reactions as they happen, frame by frame, on the atomic scale. It's like molecular cinema, and it's expanding what we know about solid structures in real time. So to wrap this up, X-ray diffraction is the key that unlocks the internal world of crystals. By analyzing how X-rays bounce off atomic planes, we can reconstruct their structure with incredible precision. Whether it's identifying a new material, confirming a crystal structure, or even revealing the shape of DNA, X-ray diffraction is one of the most powerful tools we have in solid physics. Coming up next, we dive into what happens when things aren't perfect. Crystal defects and imperfections are where materials start to show their personality. Crystal defects and imperfections. Alright, so we've just explored how perfect crystal structures are revealed through X-ray diffraction. Beautiful, symmetric, and orderly. But let's be real for a second, nature isn't always that neat. In fact, real-world crystals are full of little hiccups and disruptions, and believe it or not, that's not a bad thing. These hiccups are called crystal defects, and they play a huge role in determining the properties of materials. In fact, sometimes it's the imperfections that make a solid useful, whether it's a silicon chip in your phone or the strength of steel in a bridge. So, what exactly are crystal defects? In solid physics, defects refer to deviations from the ideal, perfectly repeating atomic pattern in a crystal lattice. And these aren't rare. Every real material has them. Defects can affect electrical conductivity, mechanical strength, chemical reactivity, and even how a material grows or deforms. So yeah, they matter a lot. Let's break this down into categories. We usually classify defects by their dimensionality: point defects, line defects, and planar defects. Each one messes with the lattice in a different way, and together, they give us a complete picture of how materials behave in the real world. First up, point defects. These are zero-dimensional, meaning they happen at or around a single point in the crystal. The most common types are vacancies, where an atom is missing from its normal lattice site. Imagine a neat row of seats at a stadium and one empty chair. That's a vacancy. Interstitials, where an extra atom squeezes into a space that's not meant for it. It's like someone sneaking into that same stadium and sitting in the aisle. Substitutional defects, where a foreign atom replaces a host atom in the lattice. This is super common in alloys. For example, in brass, some of the copper atoms are replaced by zinc atoms. These point defects can be naturally occurring due to thermal vibrations. Yes, atoms do jiggle at all times, or they can be introduced intentionally, like when we dope semiconductors with impurities to control their electrical properties. We'll go deeper into that in later sections, but just know that point defects are the smallest building blocks of imperfection. Next, let's talk about line defects, also known as dislocations. These are one-dimensional defects that involve a line of atoms being out of place in the lattice. There are two main types: edge dislocation, where an extra half plane of atoms is inserted into the crystal. Imagine trying to tile a floor and slipping in an extra row halfway through. Now every row above it is misaligned. Screw dislocation, where the layers of atoms spiral around an imaginary axis, like a parking garage ramp instead of flat floors. Dislocations are the primary reason why metals can bend without breaking. When you apply a force, these dislocations move, allowing the material to deform plastically rather than shatter. But too many dislocations can weaken a material or cause it to behave unpredictably. Moving on, we've got planar defects, which are two-dimensional. These include grain boundaries, which are the interfaces where two differently oriented crystals meet. Most metals and ceramics are polycrystalline, meaning they're made up of many tiny grains packed together. The boundaries between them are like borders between countries. They can restrict movement of atoms and electrons. Twin boundaries, which occur when one part of the crystal is a mirror image of another. These can strengthen materials by blocking dislocation motion. Stacking faults, where the regular stacking sequence of atomic planes is interrupted. These are common in materials with close, packed structures like face-centered cubic crystals. Each type of defect contributes in its own way. For instance, grain boundaries can make materials stronger, but also more brittle. Vacancies can speed up diffusion, which is super helpful in processes like sintering or in battery materials where ions need to move quickly. And substitutional atoms in semiconductors. They're the reason your phone even works. Now, here's a fun twist. Not all defects are bad. In fact, many of them are engineered on purpose to give materials the properties we want. Think about tempered glass. It's made by rapidly cooling the surface of the glass, which locks in stresses and introduces defects that actually make it stronger and more resistant to breaking. Or look at silicon chips, where introducing tiny amounts of impurity atoms, also a form of defect, makes them conductive and usable in circuits. There are also thermal defects, which are temperature dependent. At any non-zero temperature, atoms vibrate, and some can jump out of place, creating vacancies and interstitials. This means that as temperature increases, so does the concentration of defects. That's why materials often become more reactive, more conductive, or less structurally sound when heated. One more fascinating aspect: color centers. These are defects in ionic crystals that absorb specific wavelengths of light, giving the material color. For example, when you expose sodium chloride else table salt to radiation, it can trap electrons at vacant chloride ion sites, creating what's called an F center. This can turn the salt yellow or even purple, depending on the defect and the light. Scientists use techniques like scanning electron microscopy, transmission electron microscopy, and X-ray topography to study these defects. They can zoom in at the atomic level and literally see where atoms are missing, misaligned, or replaced. It's like CSI for crystals. So to wrap it up, Crystal defects and imperfections are not just random flaws. They're fundamental to how materials function. Whether it's the strength of a bridge, the efficiency of a solar panel, or the durability of a smartphone screen, defects are often what make it all possible. Understanding them gives us the power to tweak, enhance, and even reinvent the materials we rely on every day. Coming up next, electrical properties of solids, where we'll see how electrons move Ls or don't move in different types of materials, and why that makes all the difference in modern tech. Electrical properties of solids. Now that we've seen how defects can shape a material's personality, let's flip the switch, literally, and talk about electrical properties of solids. This is where solid physics gets super practical. From light bulbs to laptops, every electronic device in your life depends on how well solids can carry electric current. And spoiler alert, not all solids behave the same way when electricity comes into play. So first things first, what does it mean for a solid to conduct electricity? At its core, electrical conductivity is the ability of a material to allow electrons to move freely through it. If electrons can move easily, the material is a good conductor. If they're stuck in place, it's an insulator. And if they kind of move, but only under certain conditions. Now we're talking about semiconductors. Let's break it down into the big three: conductors, insulators, and semiconductors. Starting with conductors, the all-stars of electricity flow. Metals like copper, silver, and gold are classic examples. In these materials, the outermost electrons of the atoms, called conduction electrons, aren't tightly bound. Instead, they form a sort of sea of free, moving charge that can flow when an electric field is applied. That's why copper wires are everywhere in electrical circuits. It's cheap, it's abundant, and it lets electrons cruise through with barely any resistance. In solid physics, we often describe this using the free electron model, which we'll go deeper into in the next section. But the key idea is that in a metal, these free electrons don't need much encouragement to move. There's no significant energy barrier stopping them, so even a small voltage can get them going. Now on the flip side, we've got insulators. These are materials like rubber, wood, glass, or diamond, things that don't conduct electricity under normal conditions. Why not? Because their electrons are locked up. In insulators, there's a huge gap between the energy levels that electrons occupy, called the valence band, and the levels where they could be free to move, called the conduction band. This energy difference, known as the band gap, is just too big for electrons to jump across on their own. Imagine trying to leap across a canyon that's way too wide. You're just not making it. That's what electrons in insulators are up against. They'd need a massive amount of energy to break free. And that's why current doesn't flow. And right in between these two extremes are the semiconductors, materials like silicon and germanium. These are the sweet spot. In semiconductors, the band gap exists, but it's small enough that electrons can sometimes make the jump, either due to thermal energy, just heat from the surroundings, or a little extra push from an external voltage. Some electrons get promoted into the conduction band and become mobile. This is what makes semiconductors so special. They're not always conducting, but under the right conditions, they absolutely can be. Even more interesting, we can tweak their electrical behavior in really precise ways. That's where doping comes in, which we'll get to later. Now, electrical properties aren't just about how many electrons are free to move. It's also about how easily they can move once they're free. This is described by something called mobility, which tells us how quickly an electron moves through the lattice when an electric field is applied. If electrons are constantly scattering off atoms or defects, their mobility drops, and so does conductivity. The overall conductivity of a material depends on two main things: the number of charge carriers, like electrons or holes, and their mobility. In metals, there are lots of carriers and pretty good mobility. In insulators, almost no carriers. And in semiconductors, the carrier concentration can be adjusted, which is why we use them in all our smart devices. Let's also talk about resistivity, which is just the inverse of conductivity. High resistivity means the material resists the flow of current, like rubber. Low resistivity means current flows easily, like silver. This is how we classify materials when designing circuits or devices. Do we want the material to carry current, block it, or control it? One more fascinating detail: electrical conductivity also changes with temperature, but not in the same way for all materials. In metals, as temperature goes up, conductivity usually goes down. That's because the atoms start vibrating more and the free electrons get scattered more often. More scattering means lower mobility. But in semiconductors, conductivity increases with temperature. Why? Because more thermal energy means more electrons can jump across the band gap into the conduction band. It's kind of the opposite behavior of metals, which makes semiconductors especially useful in temperature-sensitive applications. And while we're at it, let's not forget about superconductors. These are special materials that, when cooled below a certain critical temperature, suddenly lose all electrical resistance. Current can flow through them indefinitely without any energy loss. We'll get into that later too, but it's another mind-blowing twist in how solids can behave electrically. So to sum it all up, the electrical properties of solids depend on how easily electrons can move, which depends on the structure of the energy bands inside the material. Metals let electrons flow freely, insulators hold them tight, and semiconductors play in the middle ground, letting us control how much current flows. This simple concept, how electrons move, drives everything from light switches to microprocessors. Coming up next, we'll zoom in on the free electron theory, where we'll treat electrons like a gas and start building a model for why metals conduct the way they do. Free electron theory. We've talked about how electrons flow in different types of solids, and now it's time to take that idea a step further. Let's zoom in on free electron theory, which is basically the first serious attempt at explaining why metals are such good conductors. It's simple, powerful, and honestly, kind of brilliant for something that was cooked up nearly a century ago. So, here's the big idea: in a metal, atoms are arranged in a regular crystal lattice, and their outermost electrons, the ones in the highest energy levels, are not tightly bound to any one atom. Instead, they're free to move around. That's where the term free electrons comes from. The theory treats these electrons almost like gas particles zipping around inside a box, bouncing off the walls and occasionally each other. Think of it like this: imagine a giant ball pit, but instead of kids, you've got electrons bouncing freely between the walls. The walls are the boundaries of the metal, and those little collisions and movements represent what's happening inside the solid. These electrons don't care about the individual atoms anymore. They just roam the space like they're on vacation. This simple picture helps explain a lot about how metals conduct electricity and heat. Now, this whole model is called the Drude model, after Paul Drude, who introduced it around the early 1900s. It was later improved by quantum mechanics, but we'll get to that in a bit. For now, we're sticking to the basic classical physics plus some assumptions about electrons. So, what does the Drude model say? First, it assumes that the free electrons move in straight lines until they collide with something, usually the vibrating atoms in the lattice. These collisions slow the electrons down and create electrical resistance. It also says that when an electric field is applied, the electrons are nudged in the opposite direction, creating a net flow of current. It's like giving all the electrons a little push. They still bounce around randomly, but now they have a slight drift in a certain direction. That drift is what we measure as electric current. This model does a pretty good job explaining some basic things like Ohm's law, the one that says voltage equals current times resistance. The Drude model makes that relationship feel intuitive. Increase the voltage, and the electric field gets stronger, so the electrons drift faster, and current goes up. It also does a decent job of explaining thermal conductivity in metals. Remember, the same free electrons that carry electrical current can also carry thermal energy. When one side of a metal is heated, the energetic electrons move toward the cooler side, carrying heat with them. This is why metals are not only good conductors of electricity, but also excellent conductors of heat. Copper cookware, anyone. But here's the thing, the free electron theory, while super useful, also has its limitations. For example, it assumes that all collisions are the same, that the electrons don't interact with each other, and that the atoms don't have much of an influence on the electrons' movement, other than causing the occasional collision. That's not always true, especially at smaller scales or lower temperatures, and this is where quantum mechanics comes in to tighten up the theory. The classical model doesn't explain why only certain energy levels are allowed for electrons, or why some materials are insulators even though they seem to have free electrons. To fix this, scientists added quantum ideas and developed what's now known as the quantum free electron model or Sommerfeld model. This model says that instead of moving randomly like gas particles, electrons occupy specific energy states, and they obey the Pauli exclusion principle, which means no two electrons can occupy the same state. This leads to the concept of the Fermi energy, which is basically the energy of the highest occupied electron state at absolute zero temperature. We'll explore that more in the next section, but just know that the quantum version gives us a much clearer picture of how electrons behave, especially when it comes to electrical and thermal properties. Now, what does all this theory actually do for us? Well, it helps us predict how different metals will behave when we pass current through them, heat them up, or expose them to magnetic fields. It's the foundation of how we understand resistance, conductivity, and even more advanced things like thermoelectric effects. For example, the free electron theory explains why silver is the best electrical conductor. It has lots of free electrons and very little resistance to their movement. It also helps us understand why copper is the go-to material for wires. It's not the absolute best, but it's cheap and reliable. And why aluminum is used in power lines. It's lighter than copper, even if it's a bit less conductive. We also get a clearer picture of how resistivity changes with temperature. In metals, as the temperature goes up, atoms vibrate more. These vibrations make it harder for electrons to move without bumping into things, which increases resistance. Free electron theory captures this trend, even if it doesn't get the exact numbers right. So yeah, the free electron theory might sound like a simple gas analogy, but it's the first big step in understanding the electrical life of solids. It gives us a mental model to explain why electrons move, how they create current, and what factors slow them down. It's not perfect, but it's powerful enough to lay the groundwork for everything that comes next. Up next, we'll plug into band theory of solids, where we go full quantum and see how those neat little energy bands decide whether a material becomes a conductor, an insulator, or something in between. Trust me, it's where the solid physics story really starts getting interesting. Band theory of solids. Okay, so we've talked about the free electron theory and how it gives us a first look at how electrons move inside metals. But as useful as that model is, it hits a wall when we try to explain why some materials are insulators or why semiconductors act the way they do. That's where the band theory of solids swoops in and saves the day. This is where we go full quantum and really get into the why behind the electrical behavior of solids. So, what exactly is band theory? At its core, it's all about energy levels, specifically how those levels are arranged and filled up in a solid. When atoms are isolated, like a single hydrogen atom floating in space, its electrons occupy very specific energy levels. But when you bring a bunch of atoms together, like in a crystal, those energy levels start to overlap and split due to interactions between neighboring atoms. Now imagine doing this not just for 2 or 3 atoms, but for billions, like in a real solid. The energy levels form into dense bands, basically, a whole range of allowed energy states that electrons can occupy. These bands are like highways where electrons can cruise around. But not all highways are open for traffic, and not all are equally full. The two most important bands to understand here are the valence band and the conduction band. The valence band is the highest range of energy levels that are fully occupied by electrons at absolute zero temperature. It's kind of the home base for electrons. The conduction band, on the other hand, is the next set of energy levels above the valence band where electrons can move freely and contribute to electrical conductivity. Now, here's where it gets really interesting. The gap between these two bands is what determines whether a material is a conductor, insulator, or semiconductor. Let's break that down. In conductors like copper or silver, the valence band and conduction band either overlap or are so close together that electrons can jump into the conduction band effortlessly. This means there are plenty of free electrons hanging out in the conduction band, ready to move when an electric field is applied. No energy barrier, no problem. Electrons are already in go mode. In insulators like diamond or glass, there's a huge gap, called the band gap, between the valence band and the conduction band. This gap is so wide that electrons can't make the jump under normal conditions. They're basically stuck in the valence band with no way out. This is why insulators don't conduct electricity. There are no free electrons in the conduction band to carry current. And then we have the real MVPs, semiconductors. These materials, like silicon and germanium, have a small but noticeable band gap, something like 1 electron volt. It's just big enough that electrons won't naturally jump into the conduction band at room temperature, but small enough that a little heat, light, or an external voltage can help them make the leap. Once they do, they start conducting. This controlled conductivity is why semiconductors are the backbone of modern electronics. You can tweak them, dope them, we'll get to that soon, and manipulate them to act exactly how you want in a circuit. Band theory makes all of this make sense. Here's a fun visual to help this click. Imagine 3 cities. In the conductor city, there's a massive bridge connecting the neighborhoods, the bands, and people as electrons are just walking back and forth freely. In the insulator city, there's a giant canyon between neighborhoods. No bridge, no access. And in the semiconductor city, there's a bridge, but it's narrow and guarded. You can get across, but only with a little effort or help. Another cool thing band theory explains is why materials behave differently under light. In insulators, shining light on the material doesn't do much unless the light has a ton of energy. But in semiconductors, light can excite electrons and boost them across the band gap. This is exactly how solar cells work. Light hits the semiconductor, electrons get excited into the conduction band, and boom, you've got electric current. Band theory also introduces the idea of holes. When an electron jumps from the valence band to the conduction band, it leaves behind a gap, or a hole, in the valence band. This hole acts like a positively charged particle and can also move around, contributing to current. So in semiconductors, it's not just the electrons in the conduction band doing the work. Holes in the valence band are helping too. And we're not done yet. Band theory even helps us understand temperature effects. In semiconductors, as temperature rises, more electrons gain the energy to jump into the conduction band, increasing conductivity. In contrast, in metals, Increased temperature just leads to more electron scattering and reduced mobility, which decreases conductivity. Same stimulus, opposite effects. One last mind-bending thing to mention: some materials, like topological insulators, flip the script. They behave like insulators in their bulk, but conduct electricity on their surfaces thanks to special band structures. That's more advanced stuff. But again, it all comes back to band theory. So yeah, band theory isn't just some abstract concept. It's the lens that helps us understand the entire behavior of electronic materials, from why your phone works to how solar panels generate energy, to what makes LEDs glow. This theory sits at the heart of it all. Next up, we'll talk about Fermi energy and energy bands, a topic that gives us an even deeper view into how electrons fill up these energy states and why only some of them are available for conduction. Fermi energy and energy bands. So, we've explored how energy bands shape the behavior of materials. But here's a natural follow-up: which electrons are actually doing the work. Not all of them are free to move or contribute to current. That's where Fermi energy comes in. It's like a marker that tells us which electrons are active players and which ones are just sitting tight. Let's unpack this. At absolute zero temperature, think 0 Kelvin, all the electrons in a solid fill up the lowest available energy levels. It's like stacking books from the bottom shelf up. The very top of this stack, the highest energy level occupied by electrons at 0 Kelvin, is called the Fermi energy. This isn't just a random number. It's a boundary that defines the electronic character of a material. Now, depending on the material, whether it's a metal, semiconductor, or insulator, the position of this Fermi energy varies, and it changes everything. In metals, the Fermi energy sits right in the middle of a band that isn't fully filled. That's great for conductivity. Electrons sitting near this level can be easily nudged into higher energy states when an electric field is applied. They don't need much of a push, which is why metals conduct so well. But in semiconductors and insulators, things look a bit different. The Fermi energy falls inside the band gap. That's the no electrons land between the full valence band and the empty conduction band. At 0 Kelvin, there are no electrons in the conduction band, so there's no current. But as temperature rises, some electrons gain enough energy to cross that band gap and jump into the conduction band, especially in semiconductors, where the gap is small. Here's a simple analogy. Imagine a river, the band gap separating two lands. In insulators, the river is wide and hard to cross, so barely any travelers, electrons, make it to the other side. In semiconductors, the river is narrow. Toss a few stones, thermal energy in, and you've got a bridge. In metals, there is no river at all. The lands are already connected and people are walking freely between them. In intrinsic semiconductors, the pure kind with no doping, the Fermi energy typically lies right in the middle of the band gap. It represents balance, equal opportunity for electrons to jump up into the conduction band or for holes to be created in the valence band. But the real magic happens when we start adding impurities through doping. In N-type semiconductors, we introduce atoms with extra electrons, and the Fermi level shifts closer to the conduction band. It's like raising the energy floor, making it easier for electrons to hop into the conduction zone. In P-type semiconductors, we add elements that create holes, and the Fermi level moves closer to the valence band. This movement of the Fermi energy explains why one type conducts via electrons and the other via holes. Now, it's important to understand that this Fermi energy isn't about a specific electron. It's a statistical concept. It's tied closely to something called the Fermi-Dirac distribution. This tells us the probability that a given energy level is occupied by an electron at any temperature. At absolute zero, every level below the Fermi energy is filled, and every level above is empty. But as temperature increases, the line blurs. Some electrons get excited into higher states, and the distribution starts to soften. That's why temperature affects conductivity differently depending on the material. In semiconductors, higher temperature increases conductivity because more electrons are excited into the conduction band. In metals, it's the opposite. Resistance increases because electrons scatter more as atoms vibrate more with heat. And then there's the density of states, which we'll dive into next. Fermi energy only tells us where the highest occupied level is. It doesn't tell us how many electrons are available around it. That's where density of states steps in, helping us map how many energy levels are packed into each tiny energy interval. One more angle to think about in real applications like transistors or diodes, shifting the Fermi level through doping or applying voltage is what controls how current flows. Want your transistor to turn on at a specific voltage. You're essentially manipulating the Fermi energy to align or misalign with a certain band. Engineers literally design devices around these energy levels, and even in advanced materials, like topological insulators or graphene. Understanding where the Fermi level sits is key to unlocking their exotic behaviors. In those systems, surface states and band structures get a lot more complex, but the Fermi energy is still the guiding light for predicting electronic behavior. So to sum it up, Fermi energy is the silent orchestrator. It doesn't move electrons itself, but it tells you who can move when they'll move, and how easy it'll be to make that happen. Whether you're designing a basic circuit or diving into quantum materials, this one concept shapes it all. Coming up next, we're diving into density of states and electron distribution, a perfect follow-up, because now that we know where the electrons are, it's time to see how many of them are playing the game at each energy level. Density of states and electron distribution. Now that we've talked about Fermi energy, basically the cut-off line for where electrons can chill or move, it's time to look at another key piece of the puzzle: density of states and electron distribution. These are the tools that help us map out how many electrons are available at different energy levels and how they spread themselves out. Once you understand this, you'll see exactly why some materials conduct electricity, some don't, and some only do so when they feel like it's looking at you. Semiconductors. Let's start with the density of states, often abbreviated as DOS. In solid physics, this refers to the number of available electron energy states per unit volume and per unit energy range. Sounds heavy, but think of it this way: imagine an apartment building where each floor represents a different energy level. The density of states tells you how many apartments exist on each floor. Some floors might have hundreds of units, others just a handful. In a free electron models, where we pretend electrons move freely like gas particles inside the solid, the number of available states increases with energy. That means the higher you go in energy, the more apartments you'll find per floor. So, if electrons have the energy to climb, there's plenty of room up there. But the density of states alone doesn't tell us where the electrons actually are. For that, we need to look at the electron distribution, which is governed by the Fermi-Dirac distribution. This function gives us the probability that an energy level is occupied by an electron at a given temperature. At absolute zero, everything below the Fermi energy is fully occupied and everything above it is empty. But once you raise the temperature even a little, electrons near the Fermi level start to get excited and jump to higher levels, leaving behind vacancies, or holes, in lower levels. Here's where things get fun. When we multiply the density of states by the Fermi-Dirac distribution, we get a curve that actually tells us how many electrons are present at each energy level at a given temperature. This is called the electron energy distribution. To visualize this, picture a graph where the horizontal axis is energy and the vertical axis is the number of electrons. At low temperatures, This graph is sharply cut off at the Fermi energy, like a steep cliff. But as temperature increases, the edge softens. Some electrons trickle into higher energy levels. This softening is crucial in materials like semiconductors, where the number of free charge carriers depends entirely on how many electrons make the leap into the conduction band. Let's tie this into different materials. In metals, the density of states is relatively smooth, and the Fermi energy lies within a partially filled conduction band. Because there are always available energy states nearby, even a small electric field can shift electrons into higher levels. Void, instant conduction. In semiconductors, it's a different story. There's a band gap, an energy range where no electron states exist. So at absolute zero, the conduction band is empty, but with enough thermal energy, like room temperature. Some electrons gain enough energy to cross the gap. These electrons now occupy the conduction band, and the holes they leave behind in the valence band can also move. Both act as charge carriers. Now here's the twist: the density of states in a semiconductor doesn't suddenly spike as soon as you hit the conduction band. It gradually increases with energy. That means the number of electrons in the conduction band depends not just on temperature, but also on how dense those energy levels are near the edge of the band. This is why different semiconductors, like silicon versus gallium arsenide, behave differently, even under the same temperature or doping conditions. Also worth noting is that the effective mass of the electron, which is tied to the curvature of the band structure, affects the shape of the density of states. A flatter band curve means heavier effective mass and a higher density of states, while a steeper curve means lighter mass and fewer available states. So again, we're not just talking about electrons. We're talking about how the structure of the material controls their behavior. And this doesn't just apply to electrons. Holes have their own density of states too. In p-type semiconductors, where holes dominate conduction, we care about the density of available states near the top of the valence band. In advanced materials like quantum wells, dots, or topological insulators, the density of states takes on even more exotic forms. In a quantum dot, for example, energy levels are discrete. Think of it like a small cabin instead of a high rise. Only specific energy values are allowed, and electrons can't live anywhere in between. This changes everything about how the material absorbs light, conducts current, or even stores energy. Now let's wrap it up with a simple idea: conductivity is not just about whether electrons are there. It's about whether they have somewhere to go. The combination of density of states and electron distribution tells us exactly how many electrons are able to move, how easily they can be excited, and what the overall electrical behavior of the solid will be. So the next time you flip on a light switch, power up your phone, or even stare into an LED screen, remember, it's this invisible map of energy states and electron probability that makes it all work. It's what lets electrons dance from atom to atom and bring circuits to life, intrinsic and extrinsic semiconductors. So now that we understand how electrons are distributed across energy levels and how the density of states plays into that, let's move to something that really puts all of it into action: intrinsic and extrinsic semiconductors. This is where solid physics starts feeling less like theory and more like magic we can control. Let's start with intrinsic semiconductors. These are the pure, untouched versions. Materials like silicon or germanium in their natural, undoped state. Imagine a clean playing field, no added impurities, no tricks, just a crystal lattice of atoms doing their thing. At absolute zero, intrinsic semiconductors don't conduct electricity. Why? Because the valence band is full, and the conduction band is completely empty, with a band gap in between. No electrons can jump across that energy gap without some kind of boost. But at room temperature or higher, things start to get interesting. Some electrons get enough thermal energy to jump from the valence band into the conduction band. When that happens, they leave behind holes in the valence band. And now we've got movement. Electrons in the conduction band can carry negative charge, while holes in the valence band can act like positive charge carriers. This is what we mean when we say intrinsic conduction. It's the electrical conductivity that arises purely from the thermal excitation of electrons across the band gap in an undoped semiconductor. Now, a key point here: for every electron that makes the jump into the conduction band, one hole is left behind. So the number of electrons and holes is equal. This is described by the equation n top p ni, where n is the number of electrons in the conduction band, p is the number of holes in the valence band, and ni is the intrinsic carrier concentration, which depends heavily on the material and the temperature. But here's the thing: intrinsic conduction is pretty weak. At room temperature, pure silicon has around 1 billion carriers per cubic centimeter. That may sound like a lot, but compare it to copper, which has about 100 billion free electrons in the same volume. Big difference. That's where extrinsic semiconductors come in. We take our pure semiconductor and we intentionally introduce impurities, a process called doping, to seriously boost its conductivity. And depending on what kind of impurity we add, we get either N-type or P-type semiconductors. Let's talk about M-type first. In silicon, each atom has 4 valence electrons and forms 4 covalent bonds with neighboring atoms. But if we replace a silicon atom with a group 5 element like phosphorus or arsenic, which has 5 valence electrons, we end up with 1 extra electron that doesn't fit into the normal bonding pattern. That extra electron is only loosely bound. It requires very little energy to break free and jump into the conduction band. So, even at room temperature, it's available to conduct electricity. This process introduces donor levels just below the conduction band, and as a result, the Fermi energy shifts upward, closer to the conduction band. In an N-type semiconductor, electrons are the majority carriers, holes are the minority carriers, and conductivity shoots up dramatically, even though we're talking about impurity levels as low as 1 atom per million. Now, flip the script for P-type semiconductors. Here, we dope the silicon with a group 3 element like boron or gallium, which has only 3 valence electrons. That means one of the silicon bonds is left incomplete. There's a hole where an electron should be. This hole can move through the lattice as neighboring electrons jump to fill it, leaving a new hole behind. This effectively creates positive charge carriers. In this case, the added impurities create acceptor levels just above the valence band, and the Fermi level shifts downward. In a P-type semiconductor, holes are the majority carriers, electrons are the minority carriers, and again, conductivity is massively improved. Now here's something cool. The energy gap between the donor or acceptor levels and their respective bands is tiny, just a fraction of an electron volt. That means thermal energy at room temperature is more than enough to activate these carriers. This is why extrinsic semiconductors dominate real-world applications. We can engineer them to behave exactly how we want, just by carefully controlling the type and amount of doping. Let's connect this back to what we've already learned. Remember how the Fermi energy shifts based on doping. That's what allows us to build devices like diodes, transistors, and solar cells. By joining N-type and P-type materials, we create p-n junctions, where the difference in Fermi levels causes charge carriers to move, setting up electric fields that can be used to control current flow. Also, the temperature dependence of conductivity is totally different for intrinsic versus extrinsic semiconductors. In an intrinsic semiconductor, increasing temperature creates more charge carriers. In an extrinsic one, increasing temperature can actually reduce mobility due to increased scattering, even though more carriers are still available. And just as a quick example, Modern processors, solar panels, and LEDs all rely on fine-tuned extrinsic semiconductors. From high-speed logic circuits to energy-efficient lighting, this concept is the backbone of electronics. So to wrap this up, intrinsic semiconductors are the clean, natural state. Extrinsic semiconductors are what we get when we take control and fine-tune the behavior by adding just the right kind of impurities. Together, they form the basis of modern electronic technology. Up next, we'll take this one step further and talk about doping and charge carriers, type and p-type in more detail. How it all works on the atomic level, and how we control conductivity with just a sprinkle of chemistry. Doping and charge carriers and type and p-type. Now that we've seen how intrinsic semiconductors naturally generate both electrons and holes, the next question practically asks itself, can we control that? Like, can we engineer a material to have more of one kind of charge carrier than the other? The answer is a big yes. And the process that makes it happen is called doping. This is where solid physics goes from understanding nature to actively shaping it. And the way we do it is surprisingly elegant. We introduce just a few carefully chosen atoms into a pure crystal, and suddenly, we've got a material with entirely different electrical behavior. This is the principle behind N-type and P-type semiconductors, and it's the foundation of almost every modern electronic device you can name. Let's break it down. In solid physics, doping means adding a very small amount of impurity atoms, called dopants, into an otherwise pure semiconductor like silicon. And we really mean small. A typical doping level might be just one impurity atom for every million silicon atoms. But those few atoms change the entire story. There are two main types of doping, depending on what kind of impurity we add in, type and p-type. Each one boosts conductivity in a different way by introducing a specific type of charge carrier. Let's start with N-type doping. The M stands for negative, and this type of doping increases the number of free electrons in the material. To do this, we introduce impurity atoms from group 5 of the periodic table, like phosphorus, arsenic, or antimony. These atoms have 5 valence electrons, while silicon has 4. When one of these group 5 atoms replaces a silicon atom in the crystal, it forms 4 covalent bonds with the surrounding silicon atoms, just like silicon would. But that 5th electron, it doesn't have a bond to form. It ends up loosely bound and can easily be knocked free, even by thermal energy at room temperature. Once freed, this extra electron becomes a conduction electron, able to move through the crystal when an electric field is applied. We call these dopant atoms donors, and they introduce energy levels just below the conduction band, called donor levels, because it takes only a tiny bit of energy to excite these donor electrons into the conduction band. N-type materials have a large population of mobile electrons, even at low temperatures. In this N-type setup, electrons are the majority charge carriers, holes are the minority carriers, and the Fermi level, which indicates the probability of electron occupancy, shifts closer to the conduction band. Now let's flip to p-type doping. Here the goal is to increase the number of holes, which behave like positively charged particles. To create p-type semiconductors, we add atoms from group 3 of the periodic table, like boron, aluminum, or gallium. These atoms have 3 valence electrons, so when a boron atom takes the place of a silicon atom in the crystal, it can only form 3 bonds, leaving 1 bond incomplete. That missing electron creates a hole, an empty spot that nearby electrons can move into. As electrons jump to fill that hole, they leave another hole behind, and the process continues, creating the illusion that the hole itself is moving. These group 3 elements are called acceptors because they accept electrons from the valence band. They create acceptor levels just above the valence band, which are easily filled by valence electrons, leaving behind mobile holes. In a p-type semiconductor, holes are the majority carriers, electrons are the minority carriers, and the Fermi level moves closer to the valence band. One key point that's easy to overlook: doping doesn't make the material charged overall. It still remains electrically neutral. The dopant atoms either donate or accept electrons, but the total number of protons and electrons stays balanced. What changes is the availability of mobile charge carriers. Another big factor is dopant concentration. The more dopant atoms you add, the more charge carriers you introduce. Light doping might give you moderate conductivity, while heavy doping, called degenerate doping, can actually push the material to behave almost like a metal, with the Fermi level entering the conduction or valence band itself. And just to tie this to real-world application, this isn't just theory on paper. This precise control over charge carriers is how we build the basic building blocks of electronics. For example, if you place an N-type region next to a P-type region, you create a PN junction. And that's where the magic of diodes, LEDs, and transistors happens. So, a quick recap: doping is how we control the conductivity of semiconductors by introducing impurities. N-type doping adds extra electrons via donor atoms, making electrons the majority carriers. P-type doping creates holes several via acceptor atoms, making holes the majority carriers. The type of doping shifts the Fermi energy and changes how the material conducts electricity. And all of this happens with just a few atoms per million. Coming up next, we'll see what happens when these two types meet, the PN junction. This is where static theory turns into dynamic function, and we start seeing one-way current flow, voltage drops, and the basis for how computers think. The PN junction and diodes. Once we've created N-type and P-type semiconductors, the next logical step is bringing them together. And when we do, something fascinating happens. This combination, called a PN junction, is the heart of almost every semiconductor device, from LEDs to solar cells to the processor in your phone. It's where physics starts behaving in a way that lets us control electricity, not just conduct it. So what exactly happens at a PN junction? Let's walk through it. Imagine a piece of P-type semiconductor sitting snugly against a piece of N-type semiconductor. At the moment they touch, their respective charge carriers, holes from the P side and electrons from the N side, begin to move across the junction. Electrons naturally diffuse from the N side, where they're plentiful, over to the P side, where there are fewer of them. Similarly, holes diffuse from the P side to the N side. But here's where things get interesting: as electrons cross over and recombine with holes, they leave behind positively charged donor ions on the N side. At the same time, holes recombine with electrons on the P side, leaving behind negatively charged acceptor ions. These fixed ions can't move. They're stuck in the lattice, and they create an electric field pointing from the N side to the P side. This zone near the junction, where mobile carriers have diffused away and only immobile ions remain, is called the depletion region. It's essentially a barrier. The internal electric field it creates pushes back against further carrier movement. So as diffusion tries to move carriers across the junction, the electric field resists that movement. Eventually, a balance is reached. The diffusion force and the electric field cancel each other out, and equilibrium is established. At equilibrium, you get something really cool, a built-in potential, also called a contact potential. For silicon, it's typically around 0.7 volts. This means that without applying any external voltage, the junction naturally has this tiny internal voltage built in, just from the physics of carrier diffusion and electric fields. Now, when we apply an external voltage to this junction, we can manipulate what happens at the depletion region. This is where the diode comes into play. Let's say we connect a battery so that the positive terminal touches the P side and the negative touches the N side. This setup is called forward bias. It reduces the width of the depletion region by canceling out some of the built-in potential. As that barrier narrows, Electrons from the N side gain enough energy to cross the junction and recombine with holes on the P side. Current flows easily in this direction and the diode conducts. But if we reverse the battery, positive to the N side, negative to the P side, we get reverse bias. This actually widens the depletion region, increasing the potential barrier and preventing current flow. Only a tiny leakage current gets through, usually due to minority carriers, but for the most part, the diode is off. This behavior, conducting in one direction and blocking in the other, is what makes a diode so useful. It's like a one-way valve for electricity. The mathematics behind the current flowing through a diode is described by the Shockley diode equation, written in words as current equals reverse saturation current multiplied by the exponential of charge of an electron times voltage divided by Boltzmann constant times temperature, -1. More specifically, I equals I naught multiplied by open bracket exponential of Q times V divided by K times T -1, close bracket. Where I is the current through the diode, I naught is the reverse saturation current, a very small current that flows in reverse bias. Q is the charge of an electron, V is the voltage applied across the diode, K is the Boltzmann constant, and T is the absolute temperature in Kelvin. This equation tells us that in forward bias the current increases exponentially with applied voltage, while in reverse bias it stays extremely small. That's exactly the behavior we see in a working diode. Now, this same p-n junction principle is used in all kinds of real-world applications. In LEDs, light-emitting diodes, when electrons and holes recombine at the junction, they release energy as light. In solar cells, sunlight excites electrons, and the p-n junction separates them to generate a current. Even the simplest rectifier circuits, used to convert alternating current to direct current, rely on this one-way behavior. An interesting extension of the basic p-n junction is the Zener diode, which is designed to operate in reverse bias but at a very specific voltage. When that voltage is reached, it breaks down and allows current to flow in reverse. This property makes it incredibly useful in voltage regulation circuits. Another variation is the Schottky diode, which uses a metal semiconductor junction instead of a p-n junction. It has a much smaller forward voltage drop, usually around 0.3 volts, and switches faster, making it great for high-speed electronics. Even though the p-n junction sounds simple, it's where semiconductor physics really starts turning into engineering. This tiny boundary between two doped materials is what enables diodes, transistors, sensors, solar panels, and countless other technologies. The Hall effect. If you've ever wondered how we can measure the type of charge carrier in a material, whether it's electrons or holes, or even estimate how many of them there are, the Hall effect is our go-to tool. It's one of those beautiful, experimentally simple, yet conceptually rich phenomena that links electricity, magnetism, and solid physics all in one clean shot. Let's break it down. Imagine a thin, flat strip of conducting or semiconducting material. Now connect a battery so that current flows along the length of this strip. That current is carried by charge carriers, electrons if we're dealing with N-type material, or holes if it's P-type. Now comes the twist. We place this strip in a magnetic field that points perpendicular to the current. In our setup, let's say the current flows left to right, and the magnetic field is directed straight downward through the surface. Something really interesting starts to happen. According to the Lorentz force law, any charged particle moving through a magnetic field experiences a force perpendicular to both its velocity and the magnetic field direction. So in our case, the electrons or holes moving through the strip get pushed sideways. They start drifting, not just along the strip, but also toward one edge of it. This sideways deflection causes charge to build up on one side of the material. For electrons, the left side might become more negatively charged. For holes, the right side might become more positive. Either way, this buildup of charge creates a transverse electric field across the width of the strip. Eventually, the electric force pushing the charge carriers back across the strip balances the magnetic deflection. At that point, equilibrium is reached and a steady voltage develops across the width of the material. This is called the Hall voltage. So now you have a current flowing in one direction, a magnetic field perpendicular to that, and a voltage appearing in the third, mutually perpendicular direction. That's the Hall effect. Here's what makes it especially powerful. The sign of the Hall voltage tells you whether your charge carriers are negative electrons or positive holes. If the voltage builds up on one side in a certain direction, you're looking at an N-type semiconductor. If it builds in the opposite direction, it's P-type. Now let's talk about the math behind it. But in words, as you asked. The Hall voltage is given by the formula Hall voltage equals magnetic field strength multiplied by current, divided by charge carrier density multiplied by charge of the carrier multiplied by thickness of the material. Or simply V sub H equals B times I divided by N times Q times D, where V sub H is the Hall voltage, B is the magnetic field strength, I is the current, N is the number of charge carriers per unit volume, cell also called carrier density. Q is the charge of the carriers, positive for holes, negative for electrons, and D is the thickness of the material in the direction of the Hall voltage. The beauty of this equation is that it lets us measure carrier density experimentally. Just by applying a known current and magnetic field and measuring the Hall voltage and thickness, we can solve for N, the carrier concentration. That's a huge deal in materials science and device engineering. There's another quantity that comes out of the Hall effect, called the Hall coefficient, which is just the Hall voltage divided by the product of current and magnetic field. Mathematically, Hall coefficient equals 1 divided by charge carrier density multiplied by charge of the carrier. Again, if you measure the sign and magnitude of the Hall coefficient, you know whether you've got electrons or holes and how many of them are moving through the material. This principle isn't just for textbooks. It's used in real-world sensors all the time. Hall effect sensors are used in smartphones for detecting the orientation of the magnetic field in compasses. They're used in cars to detect wheel speed, position, and crankshaft rotation. They're also crucial in robotics and industrial automation, thanks to their reliability and low cost. Another fascinating extension of the Hall effect is something called the quantum Hall effect, which shows up at very low temperatures and very high magnetic fields. Under those extreme conditions, the Hall voltage doesn't just vary smoothly, it jumps in discrete steps. These steps are quantized, meaning they occur at exact values related to fundamental constants. It's like the Hall effect goes digital. But that's a topic for later. Back to the classical Hall effect. There's one more nuance worth pointing out. In metals, where electrons are the dominant carriers, the Hall voltage is typically quite small. But in semiconductors, the lower carrier density means the Hall voltage is much more noticeable. That's why it's particularly useful in semiconductor physics, where measuring and tuning carrier properties is everything. So to wrap up, the Hall effect occurs when moving charge carriers in a material are deflected by a magnetic field, creating a voltage across the material. The direction of that voltage tells us the sign of the carriers, electrons or holes. The magnitude gives us a way to calculate carrier density. It's a practical, powerful diagnostic tool and the basis of many electronic sensors. It's one of those effects where the math, the theory, and the real-world application all line up perfectly. A little magnetic field, a steady current, and suddenly your material is talking to you and telling you exactly what's going on inside. Magnetism in solids basic concepts. Magnetism might feel like something we only encounter in fridge magnets or compasses, but at the atomic level, It's a fundamental property that tells us a lot about how solids behave. When we talk about magnetism in solid physics, we're really diving into how individual atomic moments, tiny magnetic fields created by electrons, interact with each other and respond to external magnetic fields. Let's start at the very beginning. Every electron has two key features that make it capable of generating a magnetic field: its charge and its spin. As electrons move around the nucleus of an atom, they create tiny circular currents. These currents, in turn, generate what we can think of as orbital magnetic moments. But there's more. Each electron also has an intrinsic property called spin, which you can picture, not literally, but conceptually, as the electron spinning on its own axis. That spin also contributes to a spin magnetic moment. So, in a solid, each atom, depending on how its electrons are arranged, might have a small magnetic moment. Whether or not these moments add up to a larger, observable magnetic effect depends on how the atoms are organized and how those moments interact with each other. The first key concept is magnetic susceptibility, which describes how much a material becomes magnetized in response to an external magnetic field. In words, it's the ratio of magnetization to the applied magnetic field. So, magnetic susceptibility equals magnetization divided by applied magnetic field. The unit of magnetization is typically amperes per meter, and it tells us how strongly the internal magnetic field of the material is aligned with the external one. Now, based on how materials respond to magnetic fields, we can categorize them into three broad types: diamagnetic, paramagnetic, and ferromagnetic. Let's start with diamagnetism, the most subtle of the three. Diamagnetic materials are those in which all the electrons are paired, so there's no permanent magnetic moment in any atom. When an external magnetic field is applied, it induces a tiny current in the electron orbits that opposes the applied field. This is due to Lenz's law. The result: the material gets a very weak magnetic field in the opposite direction. That's diamagnetism: weak, always repelling, and present in materials like bismuth, copper, and even water. Yes, technically, water is diamagnetic. Next up is paramagnetism. In these materials, some atoms have unpaired electrons, so they do have a net magnetic moment. But under normal conditions, these moments are randomly oriented because of thermal motion, so the material doesn't show any net magnetism. When you apply a magnetic field, however, the atomic moments start to align slightly with the field, giving rise to a weak magnetization in the same direction as the applied field. When the field is removed, the alignment disappears. Examples of paramagnetic materials include aluminum, oxygen, and some transition metal ions. Then there's the heavy hitter ferromagnetism. This is the kind of magnetism we're most familiar with. Iron, cobalt, and nickel all exhibit it. In ferromagnetic materials, atoms with unpaired electrons interact with each other through a quantum mechanical process called exchange interaction. This interaction causes neighboring magnetic moments to align in the same direction, forming what are known as magnetic domains. Within each domain, the moments are perfectly aligned, creating a strong magnetic field. When an external magnetic field is applied, these domains grow in the direction of the field, and the overall magnetization increases dramatically. Even when the field is removed, the domains often stay aligned. This is what gives permanent magnets their staying power. There's also a temperature factor here called the Curie temperature. Above this critical temperature, thermal agitation becomes strong enough to disrupt the alignment of magnetic moments, and the material loses its ferromagnetic properties, becoming paramagnetic. For iron, this happens at around 1104 Kelvin. Mathematically, the behavior of paramagnetic materials is often described using Curie's law, which in words is: magnetic susceptibility is equal to a constant Sevels called the Curie constant divided by temperature. This law tells us that as the temperature increases, the magnetic susceptibility decreases. Basically, higher thermal energy makes it harder for magnetic moments to align with an external field. So to summarize, diamagnetic materials repel magnetic fields slightly due to induced currents opposing the applied field. No unpaired electrons here. Paramagnetic materials have unpaired electrons that align with a magnetic field, but only while it's applied. Ferromagnetic materials have strong, permanent alignment of moments due to exchange interaction and can remain magnetized even without an external field. These foundational concepts are essential because everything from data storage to magnetic sensors to electric motors relies on understanding how materials respond to magnetic fields. And at the atomic level, it all comes down to spin motion and how tiny magnets, aka electrons, decide to play together. Ferromagnetism, paramagnetism, diamagnetism. When we talk about magnetism in solid physics, we're really talking about how atoms, and more specifically, the electrons inside those atoms, interact with magnetic fields. But not all materials behave the same way. In fact, depending on their atomic structure and the way electrons are arranged, solids can be classified into three main magnetic types: ferromagnetic, paramagnetic, and diamagnetic. Each one has a distinct origin, behavior, and response to external magnetic fields. Let's start with ferromagnetism, which is probably the most familiar. This is the phenomenon behind everyday magnets, the kind you stick on your fridge or use in electric motors. In a ferromagnetic material, such as iron, cobalt, or nickel, the atoms have unpaired electrons, and more importantly, those unpaired electron spins don't just float around randomly. Thanks to a quantum mechanical effect called the exchange interaction, neighboring spins tend to align in the same direction, creating regions of uniform magnetization called magnetic domains. Now, these domains exist even when there's no magnetic field applied. But when you apply an external field, the domains that are aligned with it grow larger, while others shrink. This alignment is so strong that even after removing the external field, many of the domains remain oriented, giving the material permanent magnetism. This is why you can magnetize a piece of iron and it stays magnetized. There's also an important temperature associated with ferromagnetism, known as the Curie temperature. Above this temperature, thermal energy becomes strong enough to disrupt the alignment of spins, so even a ferromagnetic material becomes paramagnetic when heated beyond this point. For iron, this Curie temperature is around 1104 Kelvin. Now, speaking of paramagnetism, this is a bit subtler. In paramagnetic materials, like aluminum, magnesium, or oxygen, there are also unpaired electrons in the atoms, so each atom has a tiny magnetic moment. But unlike ferromagnets, there's no interaction aligning the moments with each other. They're randomly oriented due to thermal agitation. However, when you apply an external magnetic field, these moments tend to align weakly in the direction of the field, giving rise to a small net magnetization. It's a temporary effect. The moment you switch off the magnetic field, the thermal energy takes over again, and the moments scatter back into random directions. So, paramagnetism is always weak and non-permanent. The magnetization of a paramagnetic material is also temperature dependent. This behavior is described by Curie's law, which states, in words, magnetic susceptibility is equal to the Curie constant divided by the temperature. This means that as temperature increases, the material becomes less magnetically responsive. The higher the temperature, the more thermal motion disrupts the alignment of spins, and the weaker the material's magnetization. Finally, let's explore diamagnetism, the simplest and yet most universal form of magnetism. Every material shows diamagnetism to some extent, but it's usually masked by stronger paramagnetic or ferromagnetic effects. In diamagnetic materials, such as bismuth, copper, graphite, and even water, all electrons are paired. This means there's no permanent magnetic moment in the atoms, So how does a diamagnetic material react to an external magnetic field? According to Lenz's law, when a magnetic field is applied, it slightly alters the orbital motion of electrons, inducing tiny currents that create a magnetic moment opposing the applied field. This leads to a very weak repulsion. That's the hallmark of diamagnetism. Materials develop a small magnetization in the direction opposite to the external field. It's a purely induced effect and disappears the moment the field is removed. It's also the only form of magnetism that doesn't depend on unpaired electrons. One of the clearest demonstrations of diamagnetism is with bismuth. If you suspend a small bismuth sample over strong neodymium magnets, it levitates slightly because of the repulsion between the induced magnetic field and the applied one. That's diamagnetism in action. To summarize the differences clearly, ferromagnetic materials have unpaired electrons and strong interactions between atomic moments, leading to permanent magnetization and magnetic domains. They show strong, persistent magnetism. Paramagnetic materials also have unpaired electrons but no interaction between moments. They align weakly with an external magnetic field and lose all magnetization when the field is removed. They show weak temporary magnetism. Diamagnetic materials have all electrons paired and generate an induced magnetic field that opposes the external one. They show very weak, repulsive, and always temporary magnetism. These three types set the stage for deeper magnetic behavior in solids. As we move further, we'll see how domain dynamics, hysteresis, and advanced concepts like antiferromagnetism and ferromagnetism build on these basic interactions. But at the core of it all, it's still electrons, their spins, their motion, and the way they respond to the invisible hand of a magnetic field that shape the magnetic identity of every material. Magnetic domains and hysteresis. To really understand how magnetism works in ferromagnetic materials, we need to zoom in, not just at the atomic level, but at how groups of atoms behave together. That's where magnetic domains come in. You can think of them as tiny regions within a solid where the magnetic moments of atoms are all aligned in the same direction, like a bunch of compass needles pointing the same way. Each domain acts like a small magnet. But here's the interesting part: in an unmagnetized ferromagnetic material, these domains are not all pointing the same way. They're randomly oriented, so their individual magnetic fields cancel each other out, and the material as a whole appears non-magnetic from the outside. It's only when you apply an external magnetic field that the story changes. Under the influence of an external field, two things start happening. First, domain walls, the boundaries between regions of different orientations, begin to shift. Domains aligned with the field start to grow at the expense of others. Second, the individual magnetic moments within domains may start to rotate slightly to better align with the field. The net effect is that the material as a whole becomes magnetized, and the more you increase the field, the more the domains reorient in that direction. Eventually, you reach a point called saturation magnetization. This is where practically all the domains are aligned with the external field, and increasing the field further doesn't result in any more magnetization. At this point, the material is fully magnetized. Now let's talk about what happens when you start decreasing the external magnetic field. You might expect the domains to immediately snap back into their original random orientations, but that doesn't happen. There's a kind of memory in the system. Even after removing the external field completely, the material retains some magnetization. This remaining magnetization is called remanence or residual magnetism. To reverse the magnetization, basically, to bring the material back to an unmagnetized state, you need to apply a magnetic field in the opposite direction. The amount of reverse field needed to bring the net magnetization to zero is called the coercive field or coercivity. When you graph this entire process, starting from zero, increasing the field to saturation, decreasing it to zero, applying a reverse field, and bringing it back. You get a loop-shaped curve called the hysteresis loop. The name, hysteresis, comes from a Greek word meaning to lag behind, and that's exactly what it describes. The magnetization of the material lags behind the changes in the external field. Let's break down the hysteresis loop in plain words. From zero to saturation, magnetization increases as domains align. Reducing the field back to zero still leaves some magnetization. This is the remnant magnetization. Applying a reverse field brings the net magnetization to zero at the coercive point. Further reverse field aligns domains in the opposite direction, reaching negative saturation. Repeating the process in the forward direction completes the loop. The area inside the hysteresis loop represents the energy lost per cycle of magnetization. This energy is usually lost as heat and is important in applications like transformers and motors, where materials are constantly being magnetized and demagnetized. Different materials have different shaped loops. Hard magnetic materials, which are used to make permanent magnets, have wide hysteresis loops with high remanence and coercivity. They resist demagnetization, which is exactly what you want in something like a refrigerator magnet or the motor in an electric vehicle. On the other hand, soft magnetic materials, used in transformer cores or inductors, have narrow loops. They can be magnetized and demagnetized quickly with minimal energy loss. It's fascinating how these microscopic domain behaviors directly influence the performance and efficiency of everyday devices. All of it boils down to how the internal magnetic structure of a material responds to external changes, and how long it remembers where it's been. So while it might seem like magnets just stick, what's actually happening is a dynamic ballet of domains flipping, stretching, shrinking, and realigning behind the scenes, leaving a trail of memory we call hysteresis. Superconductivity and the Meissner effect. Superconductivity is one of those phenomena in solid physics that sounds like science fiction at first, until you realize it's real, measurable, and absolutely fascinating. At its core, superconductivity is a quantum mechanical state in which certain materials, when cooled below a specific critical temperature, lose all electrical resistance. That means current can flow through them indefinitely without losing energy as heat. To really understand what makes this possible, let's start with what normally happens in a regular conductor like copper. As electrons flow through the metal, they scatter off of imperfections, vibrations in the lattice, which we call phonons, and other electrons. This scattering is what causes electrical resistance. The more they scatter, the more energy is lost as heat. But in a superconductor, below that critical temperature, the behavior of electrons changes completely. Instead of acting as individual particles, electrons pair up into what are called Cooper pairs. These pairs are loosely bound and act more like waves than particles. Because of the way quantum mechanics works, these Cooper pairs move in a coherent state, meaning they all share the same quantum wave function and move in sync. Now here's the wild part. Because of this coherence, Cooper pairs can flow through the lattice without scattering. They avoid all the usual resistance, causing mechanisms. It's not that they dodge them one by one. It's that the entire quantum state they're in simply doesn't interact with the lattice in the usual way. The result: zero resistance. That means if you send a current through a superconducting loop, it could, in theory, flow forever without needing any additional energy. Different materials have different critical temperatures. Traditional superconductors, like lead or mercury, need to be cooled to just a few degrees above absolute zero, around 4 Kelvin. But then there are high-temperature superconductors, like certain ceramics, which become superconducting at temperatures closer to 100 Kelvin. That's still cold, but it's achievable using liquid nitrogen instead of liquid helium. which makes a big difference for practical applications. Now let's talk about the Meissner effect, which is just as jaw-dropping. When a material transitions into the superconducting state, it not only allows current to flow with zero resistance, it also expels magnetic fields from its interior. This is something that doesn't happen in regular conductors. Imagine placing a magnet above a piece of superconducting material. As it cools below its critical temperature, it suddenly pushes the magnetic field lines out of itself, creating a repulsive force. This is why you see levitating magnets over superconductors in demonstrations. It's a direct result of the Meissner effect. The superconductor creates currents on its surface that perfectly cancel out the applied magnetic field inside, causing the magnet to float. Technically, this magnetic field expulsion occurs because the superconductor tries to maintain a zero magnetic field inside. It does this by generating surface currents that oppose any external magnetic influence. This phenomenon distinguishes superconductors from perfect conductors. A perfect conductor could carry current with zero resistance, but it wouldn't necessarily expel magnetic fields. The Meissner effect is what makes a superconductor truly unique. Mathematically, this is captured by the London equations, which describe how magnetic fields decay exponentially inside a superconductor. This decay happens over a small length scale called the London penetration depth, typically on the order of hundreds of nanometers. What makes this even more exciting is that the Meissner effect is reversible. If you raise the temperature of the superconductor above its critical point or apply a magnetic field stronger than its critical magnetic field, it reverts to a normal, resistive state and allows magnetic fields to enter again. Superconductors are already used in technologies like MRI machines, magnetic levitation trains, and particle accelerators. But research is pushing even further. Scientists are hunting for room temperature superconductors, which could revolutionize everything from energy transmission to quantum computing. To sum it up, superconductivity is not just about no resistance. It's about entering an entirely new quantum state of matter where electrical currents face no friction, and magnetic fields get kicked out of the party entirely. And the Meissner effect is that dramatic visual proof that you've entered this state. BCS Theory of Superconductivity. When we first see superconductivity in action, zero resistance, levitating magnets, it feels like magic. But behind that magical behavior lies a quantum mechanical explanation that reshaped our understanding of matter. This explanation is known as the BCS theory, named after the three physicists who developed it in 1957: John Bardeen, Leon Cooper, and Robert Schrieffer. Their work finally gave the world a microscopic explanation for superconductivity, and it earned them the Nobel Prize in Physics in 1972. To understand BCS theory, we need to go beneath the surface. Quite literally, let's begin by looking at the behavior of electrons in a normal conductor. In a typical metal, electrons are constantly being scattered. They bounce off impurities, crystal defects, and the vibrations of the atomic lattice, which we call phonons. This scattering is what causes electrical resistance. The more the lattice vibrates, especially at higher temperatures, the more the electrons get deflected and the more energy is lost as heat. But when a material is cooled below its critical temperature, something dramatic happens. It enters a superconducting phase and resistance drops to exactly zero. No matter how long the current flows, it won't degrade. So, what changed? This is where the BCS theory comes in. It proposes that below the critical temperature, electrons stop behaving like individual, repelling particles. Instead, they form Cooper pairs. Named after Leon Cooper, who first proposed the concept. At first, this sounds bizarre. Why would electrons, which naturally repel each other because they both carry negative charge, suddenly pair up? The key is the interaction between electrons and the vibrating lattice. Imagine one electron moving through the lattice. As it passes by, it pulls nearby positively charged ions slightly out of position, creating a tiny region of higher positive charge. This localized distortion doesn't disappear instantly. It lingers for just long enough to attract a second electron. So even though the electrons don't directly attract each other, they end up forming a pair because of the indirect attraction mediated by lattice vibrations or phonons. Now, these Cooper pairs aren't bound in the way we think of chemical bonds. They're extremely fragile and only exist in a specific quantum state. But here's the crucial detail: when these pairs form, they begin to act coherently. Instead of each electron doing its own thing, all the Cooper pairs behave like a single quantum wave function that spans the entire material. This changes everything. In the normal state, electrons scatter individually and lose energy. But once they form Cooper pairs and enter this collective state, they can flow without scattering. It's not that they dodge obstacles. It's that the lattice simply cannot scatter the entire wave function. It's like trying to trip a marching army with a pebble. You might nudge one foot, but the whole unit keeps moving forward. The BCS theory explains more than just zero resistance. It also accounts for the energy gap observed in superconductors. When you cool a material into the superconducting state, its electronic structure changes. There's a gap, a range of energies, between the ground state where Cooper pairs exist and the excited state where the pairs are broken and normal electrons resume motion. To break apart a Cooper pair, you need to supply a minimum amount of energy, which corresponds to this energy gap. This gap increases as the temperature decreases and vanishes at the critical temperature, where the material reverts to its normal state. It's also what gives superconductors their resistance to weak magnetic fields and thermal fluctuations. The energy needed to disrupt the superconducting state isn't readily available unless the temperature rises or the external magnetic field becomes too strong. Mathematically, the BCS theory involves some heavy-duty quantum mechanics, but at its heart, it describes a wave function that combines all the Cooper pairs into one unified state. This allows predictions of various measurable quantities like the energy gap, the critical temperature, the specific heat of the material, and even the Meissner effect, the expulsion of magnetic fields from a superconductor. In fact, one of the key successes of BCS theory was that it explained the Meissner effect naturally. The surface currents that cancel out magnetic fields arise from the same quantum mechanical coherence that makes the Cooper pairs resist scattering. So the theory didn't just explain zero resistance. It accounted for the full behavior of superconductors, both electrical and magnetic. There's also an important note about the type of materials BCS theory applies to. It works beautifully for conventional superconductors like lead, aluminum, or tin, which have low critical temperatures and behave in predictable ways. But starting in the 1980s, scientists discovered a new class of materials, high-temperature superconductors such as cuprates and iron-based compounds, that didn't fully fit into the BCS framework. These materials exhibit superconductivity at much higher temperatures, and while Cooper pairs are still involved, the mechanism might be more complex. Research is ongoing, and the full picture of high-temperature superconductivity is still developing. That said, BCS theory remains one of the most elegant and powerful examples of how quantum mechanics can explain macroscopic phenomena. It shows us that something as fundamental as electricity can take on entirely new properties under the right conditions. And it all starts with a subtle interaction between electrons and a vibrating lattice. So next time you hear about superconductors enabling magnetic levitation or lossless power grids, remember it all hinges on the fragile but fascinating dance of Cooper pairs and the quantum choreography laid out by Bardeen, Cooper, and Schrieffer. Phonons and lattice vibrations in solid physics, When we talk about vibrations of atoms in a crystal, we're not just referring to random jiggling. These vibrations are highly organized, structured, and follow the symmetry of the crystal lattice. At the atomic level, no solid is truly static. Even at absolute zero, atoms in a crystal have some residual motion due to quantum fluctuations. As temperature increases, these vibrations become more intense, and they aren't just thermal noise. They're deeply connected to the solid's physical properties. This is where the concept of phonons comes in. A phonon is a quantized mode of vibration occurring in a rigid crystal lattice, similar to how a photon is a quantized mode of electromagnetic radiation. Phonons are not particles in the traditional sense, they're quasiparticles, meaning they emerge from the collective behavior of atoms within the lattice. Think of a phonon as a packet of vibrational energy. When atoms in a lattice vibrate together in a coordinated way, that vibrational energy behaves as if it were a particle. This is a direct result of quantum mechanics being applied to classical vibrations. To see how this happens, imagine atoms in a crystal connected by springs. When one atom moves slightly, it pulls on its neighbors, which causes a chain reaction. The motion propagates through the lattice as a wave. In classical physics, we would describe this using wave equations, with frequency and wavelength, depending on how stiff the springs are and how heavy the atoms are. But when quantum mechanics enters the picture, this vibrational wave can only have specific energy levels, which are quantized. Each quantum of vibrational energy is a phonon. These phonons come in two main types: acoustic phonons and optical phonons. Acoustic phonons are low-energy vibrations where atoms move in phase with each other. Similar to sound waves traveling through the solid, these are the vibrations responsible for transmitting sound, and also for a significant part of heat conduction in insulators. Optical phonons, on the other hand, involve atoms in the basis of the unit cell moving out of phase with one another. These typically occur at higher frequencies and are often excited by electromagnetic radiation, hence the term optical. The mathematical treatment of phonons starts with modeling the crystal as a series of masses connected by springs. In a one-dimensional chain, each atom interacts with its neighbors through harmonic forces. Solving the equations of motion for this system gives a set of allowed vibrational frequencies. A phonon dispersion relation, which tells us how the energy of a phonon depends on its momentum, or wave vector. In 3 dimensions, this becomes more complex but follows the same basic principle. What makes phonons so important in solid physics is that they interact with everything, with electrons, with other phonons, and with boundaries and defects in the material. For instance, when an electron travels through a crystal and encounters a phonon, it can absorb or emit that phonon. This interaction causes the electron to scatter, and it's one of the key mechanisms behind electrical resistance at higher temperatures. The more phonons there are, which increases with temperature, the more likely it is that electrons will scatter, and the greater the resistance becomes. Phonons are also the main carriers of thermal energy in non-metallic solids. In metals, electrons dominate thermal conduction, but in insulators, where free electrons are absent, phonons take over. They move heat from hot regions to cold regions by transferring vibrational energy. However, their efficiency depends on how freely they can move. If a crystal has a lot of defects, impurities, or grain boundaries, phonons will scatter more, and thermal conductivity will be lower. Another fascinating aspect of phonons is their role in quantum phenomena like superconductivity. In conventional superconductors, as described by BCS theory, phonons are the glue that binds Cooper pairs together. An electron distorts the lattice slightly, creating a phonon, and that phonon attracts another electron, indirectly forming a pair. Without phonons, the lattice wouldn't mediate this interaction, and superconductivity wouldn't occur. Phonons also play a major role in optical properties. In some materials, when light interacts with the lattice, it can excite optical phonons. This leads to phenomena like Raman scattering, where incoming photons lose or gain energy by creating or absorbing phonons, shifting the wavelength of the scattered light. By analyzing these shifts, researchers can study lattice vibrations, molecular bonds, and even detect stress or disorder in crystals. At higher temperatures, phonon-phonon interactions become more significant. These are anharmonic effects, meaning the restoring force is no longer perfectly proportional to displacement. When phonons interact, they can combine, split, or scatter off each other, which changes the way heat and sound propagate. This is also why specific heat behaves differently at high temperatures compared to low ones. Something we'll dive deeper into when discussing the Debye and Einstein models. Finally, phonons have momentum and energy, just like particles. However, because they arise from periodic structures, their momentum is quasi-momentum, confined within the boundaries of the first Brillouin zone. This leads to the concept of phonon band structures, which mirror the idea of electronic band structures. Just like electrons, phonons occupy allowed energy bands based on the symmetry and spacing of the crystal lattice. In summary, phonons are central to the behavior of solids. They explain how solids conduct heat, how they vibrate, how electrons scatter, and how superconductivity can even arise. They're a perfect example of how quantum mechanics turns collective, wave-like behavior into something we can treat like a particle, making them one of the most important quasiparticles in condensed matter physics. Specific heat Debye and Einstein models in solid physics. One of the most revealing thermodynamic properties of a material is its specific heat, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. At first glance, this might seem like a straightforward property, but when you look at how solids behave at low and high temperatures, you'll notice that the pattern of specific heat isn't as simple as it seems. Historically, before quantum mechanics was introduced, physicists used what's known as the DeLong-Petit law, which predicted that the molar specific heat of a solid would be roughly constant, around 3 times the gas constant, or 3R. This made sense at room temperature for many solids, but completely failed at low temperatures, where experiments showed specific heat dropping off dramatically instead of staying flat. This deviation signaled that classical physics wasn't enough to explain what was happening inside the solid. This led to the development of quantum models to explain how specific heat behaves. Specifically, the Einstein model and later, the more refined Debye model. Let's begin with the Einstein model. Albert Einstein proposed this model in 1907 by applying quantum theory to the vibrations of atoms in a crystal lattice. The basic assumption was that every atom in the solid vibrates independently and at the same frequency, like tiny identical harmonic oscillators. This means that energy is not continuously variable, but comes in discrete packets, or quanta. Einstein derived an expression for specific heat using the concept of quantized energy levels. As temperature increases, more of these vibrational energy levels become accessible to atoms, leading to an increase in specific heat. The model successfully explained why specific heat decreased at low temperatures. It captured the quantum nature of atomic vibrations. The specific heat in the Einstein model depends on the Einstein temperature, a characteristic temperature related to the frequency of these vibrations. As the temperature drops below this value, fewer atoms have enough thermal energy to reach higher vibrational states, and thus specific heat falls. However, the Einstein model had a limitation. It assumed all atoms vibrate at the same frequency, which is not realistic in an actual solid where a whole range of vibrational frequencies exists due to the different ways atoms can move, some fast, some slow, some in sync, some not. That's where the Debye model came in. Peter Debye introduced his model in 1912 to improve upon Einstein's approach. Instead of assuming a single vibration frequency, Debye treated the solid as a continuum of vibrations, introducing the idea of a phonon spectrum, a distribution of vibrational modes with varying frequencies up to a maximum frequency called the Debye frequency. This spectrum includes both low-energy and high-energy vibrations, with the distribution weighted according to the density of states of the phonons. Debye's key insight was that at very low temperatures, only low-frequency or long-wavelength phonons are excited because the higher energy vibrations require more thermal energy than is available. These low-energy phonons dominate the specific heat behavior, and this leads to a famous result in solid-state physics at low temperatures. The specific heat of a solid is proportional to the cube of the temperature. Mathematically, this is expressed as specific heat being proportional to temperature raised to the power of 3, or C is proportional to T cubed. This was a huge breakthrough because it matched experimental data perfectly, especially the observed T cube dependence at low temperatures, something the Einstein model failed to predict. At high temperatures, the Debye model also converges with the Dulong-Petit law, predicting a constant specific heat, just like classical physics would expect. This dual accuracy, matching both low and high temperature behavior, is what made the Debye model the standard for understanding specific heat in solids. The Debye temperature, a critical parameter in the model, is different for each material and indicates the point where quantum effects begin to significantly affect specific heat. For example, lead has a relatively low Debye temperature, meaning quantum effects fade at lower temperatures, while diamond has a very high Debye temperature, so quantum effects persist even at room temperature. Beyond explaining temperature-dependent specific heat, the Debye model also helped clarify the vibrational density of states in a solid. That is, how many vibrational modes exist at a given frequency. The model assumes a linear relationship between frequency and wave vector at low frequencies, similar to sound waves, and integrates over all modes to find the total heat capacity contribution. Both Einstein and Debye models use simplifications, but they revealed how classical physics breaks down when dealing with atomic scale phenomena. By applying quantum ideas to vibrations in solids, these models laid the groundwork for more advanced concepts like phonons, thermal conductivity, and the quantum nature of energy storage in materials. It's also worth noting that today, with more powerful computational tools and precise experimental data, modern physicists often use a combination of models, or even fully numerical simulations, to predict heat capacities, especially in complex or disordered solids. But the conceptual foundations laid by Einstein and Debye remain central to how we understand thermal behavior in solids. In summary, the Einstein model introduced the idea that vibrational energy levels in solids are quantized, which explains the drop in specific heat at low temperatures. The Debye model expanded on this by considering a range of vibrational frequencies and successfully matched both the low temperature and high temperature behavior observed in experiments. Together, these models show how quantum mechanics reshapes even something as seemingly simple as heating up a solid. Thermal conductivity in solids. Thermal conductivity in solids is all about how heat moves through a material, and it's one of the most important properties in solid physics, especially when you're dealing with devices, structures, or even materials that need to handle temperature changes. At its core, thermal conductivity tells us how efficiently a material can transport heat from one point to another. In solids, this process doesn't happen by hot atoms flying around like in gases. Instead, it's mainly carried out by two key players, phonons, and in the case of metals, free electrons. Let's start with phonons. In insulators and most semiconductors, phonons, those quantized vibrations of atoms in a crystal lattice, are the dominant heat carriers. When one part of a solid heats up, atoms vibrate more intensely in that region. These vibrations create phonons that travel through the lattice, transferring thermal energy to cooler areas. The more efficiently phonons can move without scattering, the higher the thermal conductivity of the material. Now, this movement isn't completely smooth. Phonons don't travel forever in a straight line. They scatter off impurities, grain boundaries, other phonons, and especially off defects in the crystal structure. This is where the mean free path comes in. It's the average distance a phonon travels before it gets scattered. The longer the mean free path, the better the thermal conductivity. So materials that are highly ordered, pure, and have fewer imperfections allow phonons to carry heat more efficiently. One useful equation to understand phonon-based thermal conductivity is based on the kinetic theory of gases, adapted for solids. Thermal conductivity denoted by K is approximately proportional to 1/3 the product of the specific heat, the phonon velocity, and the phonon mean free path. So, written in words, K equals 1/3 multiplied by specific heat multiplied by phonon velocity multiplied by mean free path. This gives a basic idea of what factors influence thermal transport. More heat capacity, faster phonons, and fewer collisions all result in better heat conduction. In metals, the story shifts slightly. While phonons still contribute to thermal transport, free electrons play a much larger role. These electrons not only conduct electricity, but also carry heat, since they can move freely through the lattice and transfer energy rapidly. In fact, in good metals like copper or silver, electrons dominate the thermal conductivity. This connection between electrical and thermal conductivity in metals is captured in the Wiedemann-Franz law, which states that the ratio of thermal conductivity to electrical conductivity is proportional to the temperature. This means that if a metal is good at conducting electricity, it's usually also good at conducting heat. But even electron-based thermal conductivity isn't immune to scattering. Electrons scatter off phonons, impurities, and other electrons, which can limit how far and fast they can carry heat. At low temperatures, phonon scattering is reduced, so electron contribution becomes even more prominent in metals. That's why metals like silver and gold, which have very few impurities and a lot of mobile electrons, are among the best thermal conductors we know. Another important factor that affects thermal conductivity is temperature itself. In metals, thermal conductivity typically decreases with temperature. This might sound counterintuitive, but here's why it happens. As temperature increases, lattice vibrations become more intense, which increases phonon-electron scattering. This makes it harder for electrons to move freely, reducing their ability to conduct heat. In contrast, in insulators and semiconductors, thermal conductivity usually increases with temperature up to a certain point, then starts decreasing due to increased phonon-phonon scattering, a process known as umklapp scattering. This is a type of phonon interaction where two phonons collide and produce a third that effectively reverses the momentum, acting as a roadblock to heat flow. One standout material in thermal conductivity discussions is diamond. Despite being an electrical insulator, diamond has incredibly high thermal conductivity, even higher than most metals. This is because of its strong covalent bonding, light carbon atoms, and extremely well-ordered crystal structure, which allow phonons to travel long distances with minimal scattering. It's why diamond is used in high-end thermal management applications, like heat spreaders in electronics. On the flip side, materials like glass and rubber have very low thermal conductivity. Their atomic structure is amorphous, meaning there's no long-range order. This causes phonons to scatter constantly, limiting their ability to transport heat. Similarly, materials with lots of defects or grain boundaries, like polycrystalline ceramics, have lower thermal conductivity than their single crystal counterparts. Another fascinating development in recent decades has been nanostructuring, the ability to engineer materials at the nanoscale to control thermal transport. By introducing nanolayers, nanoparticles, or superlattices, scientists can manipulate how phonons move, either enhancing or suppressing thermal conductivity based on the application. This is crucial in areas like thermoelectric materials, where low thermal conductivity is desired to maintain a temperature gradient and convert heat into electricity efficiently. Thermal conductivity is also critical in everyday technologies. In electronics, efficient heat removal prevents overheating and failure of microchips. In building insulation, low thermal conductivity materials are chosen to keep heat from escaping. In aerospace and nuclear industries, materials must maintain stability under extreme thermal loads. And in superconductors, heat transport plays a key role in managing the transition to zero resistance. In summary, thermal conductivity in solids is governed by how well phonons and electrons can move thermal energy through the lattice. It depends on temperature, structure, purity, and the type of material. Phonons dominate in insulators, electrons take over in metals, and both are influenced by scattering and structural order. Whether we're trying to dissipate heat quickly or trap it in, understanding the mechanics of thermal conduction is essential for designing materials that perform the way we need them to. Dielectrics and polarization. When you place a material in an electric field, not all of them behave the same. Metals, as we know, allow free movement of charges. They conduct. But what about materials that don't? This brings us into the world of dielectrics. Materials that are electrical insulators but respond to electric fields in a very particular way. Instead of allowing current to flow, dielectrics adjust internally. Their molecules become slightly distorted, leading to an important phenomenon known as polarization. In solid physics, dielectric materials are crucial in everything from capacitors to sensors to gate insulators in transistors. Their main feature is their ability to store electric energy through this process of polarization. So, what does polarization mean at the atomic level? In the simplest terms, it's the alignment or displacement of bound charges within a material. Atoms or molecules within a dielectric aren't perfectly symmetrical. When you apply an external electric field, the positively charged nucleus and the negatively charged electrons shift slightly in opposite directions. This creates tiny electric dipoles, even if the material was originally neutral overall. There are several types of polarization mechanisms, depending on the frequency of the applied field and the material's structure. The most basic is electronic polarization, where the electron cloud around a nucleus gets distorted by the field. Then there's ionic polarization, seen in materials with positive and negative ions. Here, the entire ion shifts position relative to its neighbors. In some materials, you also get orientational polarization, where molecules with permanent dipole moments, like water, physically rotate to align with the field. And finally, there's interfacial polarization, which happens in heterogeneous materials, especially when there are trapped charges at boundaries. To quantify how much a dielectric responds to an electric field, we use a property called the dielectric constant, also known as the relative permittivity. This value tells us how much the material amplifies the capacitance of a system compared to vacuum. A higher dielectric constant means a stronger ability to polarize in response to the field, which translates to greater energy storage. Now, let's connect this to a fundamental relationship in electromagnetism. The electric displacement field, written as D in equations, is equal to the permittivity of free space multiplied by the electric field, plus the polarization. Or, in words, electric displacement equals vacuum permittivity times electric field plus polarization. This links the applied field, the vacuum behavior, and the material's response through polarization. One key thing to remember is that polarization isn't static. if you apply a changing electric field. For instance, an alternating current. The dipoles try to realign with the field as it switches direction. But they can't keep up indefinitely. At higher frequencies, different types of polarization begin to drop out. Electronic polarization holds up even at optical frequencies, but ionic and orientational polarization lag behind and eventually vanish. This frequency-dependent behavior is why dielectric properties are not constant. They change with how fast the electric field is oscillating. Also, dielectric behavior is temperature sensitive. At higher temperatures, thermal agitation can disrupt the alignment of dipoles, reducing overall polarization. This is especially noticeable in materials with orientational polarization. Their molecules become too chaotic to align effectively. Now, when a dielectric is placed between two plates of a capacitor, something fascinating happens. The field within the dielectric becomes weaker than the applied field. This is because the polarization creates an opposing internal field that partially cancels the external one. As a result, for a given voltage, the capacitor can now store more charge. That's why inserting a dielectric increases the capacitance. The material helps store more energy without increasing the physical size or voltage. A special class of dielectrics worth mentioning is linear dielectrics. These are materials where polarization is directly proportional to the applied electric field. This proportionality is described by the electric susceptibility, which is a measure of how easily the material can be polarized. Non-linear dielectrics exist too, where the relationship between field and polarization gets more complicated, often seen in materials used for switching or tunable devices. Then we have dielectric breakdown, a critical point where the material can no longer resist the electric field. If the field becomes too strong, it rips electrons free from atoms, turning the insulator into a conductor and permanently damaging the material. The breakdown strength, measured in volts per meter, is a key property of any dielectric and determines how much voltage it can handle safely. In practice, choosing the right dielectric involves balancing many properties: high dielectric constant for good energy storage, low dielectric loss for minimal energy dissipation, high breakdown strength for reliability, and thermal stability to ensure performance under varying temperatures. Dielectrics are not just theoretical curiosities. They're at the heart of technologies like capacitors, which rely entirely on dielectric materials to function. In microelectronics, thin films of silicon dioxide or high-K materials act as insulators in transistors. In RF circuits and antennas, dielectric substrates shape signal propagation. And in medical imaging, dielectric behavior helps form the basis of diagnostic tools like MRI. So to summarize, dielectrics are insulating materials that don't conduct electricity, but they respond to electric fields through polarization. This internal rearrangement of charge lets them store electric energy, influence electric field distribution, and control capacitance. Their performance depends on structure, frequency, temperature, and purity. Understanding how and why they polarize allows us to design more efficient, more stable, and more powerful electronic systems. Optical properties of solids. When we talk about the optical properties of solids, we're diving into how materials interact with light, how they absorb it, transmit it, reflect it, and even bend or slow it down. These interactions aren't just skin deep. They come from the fundamental electronic and structural properties of the solid. Whether it's the clear glass in your windows, the shiny metal of a mirror, or the deep color of a gemstone, all of that is dictated by how light and matter talk to each other on the atomic level. Let's start with the most basic question. What happens when light hits a solid? Light is an electromagnetic wave. It carries oscillating electric and magnetic fields. When it encounters a solid material, those electric fields interact with the electrons inside the solid. Depending on the energy of the light and the electronic structure of the material. A few different things can happen. The light might be absorbed, reflected, transmitted, or even scattered. The most important factor that determines a material's optical behavior is its electronic band structure. Specifically, the energy gap between the valence band and the conduction band. If the energy of the incoming photons matches the energy gap, electrons can absorb the photon energy and jump from the valence band to the conduction band. This is called optical absorption. In metals, there are free electrons everywhere, so they can absorb light of almost any frequency. But they also reflect most of it. That's why metals like silver and aluminum are shiny. Their sea of free electrons quickly respond to the oscillating electric field of light and reflect it back. This makes metals good reflectors but poor transmitters. In insulators and semiconductors, the story is a bit different. These materials have a band gap. The size of that gap determines what part of the electromagnetic spectrum they can interact with. For example, if the band gap is larger than the energy of visible light, the material appears transparent like quartz. If the gap is just right, as in semiconductors like silicon, the material can absorb certain wavelengths while letting others pass or reflect, which is why silicon wafers appear dark. Now, how do we quantify all this? One of the most important quantities is the complex refractive index, which has two parts. The real part describes how fast light travels through the material. This is what causes refraction or bending of light. The imaginary part relates to absorption, how much the light gets attenuated as it moves through the solid. Together, they tell us how much light slows down, bends, and fades inside a material. You've probably heard of Snell's law, the rule that governs how light bends when it goes from one material to another. It's written as the refractive index of the first medium multiplied by the sine of the angle of incidence equals the refractive index of the second medium multiplied by the sine of the angle of refraction. This bending happens because light changes speed in different materials. In solids, the denser the material, optically speaking, the slower the light travels. Another important concept is the absorption coefficient. This tells us how quickly light intensity drops as it moves through a material. It's often written in exponential form, where intensity decreases exponentially with depth into the material. The higher the absorption coefficient, the more opaque the material is at that specific wavelength. Then there's reflectivity, which is the fraction of incoming light that bounces off the surface. This depends not just on the material, but also on surface conditions, angle of incidence, and even polarization of the light. Highly polished metals reflect a lot. On the other hand, matte surfaces scatter light in different directions, leading to diffused reflection. Some materials also exhibit a property called luminescence. They absorb energy and re-emit it as light, often at a different wavelength. If this happens almost instantly, we call it fluorescence. If there's a noticeable delay, it's phosphorescence. These effects arise from electrons relaxing from excited states back to lower energy states, and they play a huge role in things like LED screens, glow, in the dark materials and biological imaging. Let's not forget about photoconductivity, a phenomenon where the electrical conductivity of a material increases when it's exposed to light. This happens because light excites electrons across the band gap, creating free charge carriers. This effect is the core idea behind light sensors and photovoltaic cells. In semiconductors, optical absorption can be direct or indirect, depending on whether the electron transition across the band gap conserves momentum. In direct band gap semiconductors like gallium arsenide, photons can be absorbed directly to excite electrons. In indirect band gap materials like silicon, a phonon lattice vibration is also needed to conserve momentum. This makes indirect semiconductors less efficient at absorbing and emitting light, which is why silicon isn't used in LEDs, Even though it's great for electronics, temperature also affects optical properties. As temperature rises, band gaps can shrink slightly, changing the absorption spectrum. Lattice vibrations increase, leading to more scattering of light, especially in non-crystalline materials. That's why some materials look more opaque or hazy when heated. And there's more. Some solids can change their optical properties in response to electric or magnetic fields. These are called electro-optic and magneto-optic materials. Liquid crystals in displays, for example, realign under electric fields to modulate light transmission. Faraday rotators use magneto-optic effects to rotate the plane of polarization of light. One advanced concept is optical anisotropy, where a material's response to light depends on the direction of the light wave's travel or polarization. Birefringent materials, like calcite, split a light beam into two rays with different velocities, used widely in optical instruments and polarizers. In practical applications, the optical properties of solids are used in lenses, coatings, filters, lasers, fiber optics, solar cells, and much more. Engineers and scientists choose or design materials based on these properties to control light in precise and innovative ways. In summary, the way solids interact with light depends on their electronic structure, crystal order, and the frequency of the incoming radiation. From reflection and refraction to absorption and emission, every optical property we observe stems from how atoms and electrons respond to electromagnetic waves. Understanding these principles allows us to shape the world of optics, from simple glasses to complex photonic devices. Piezoelectric and ferroelectric materials. Let's talk about materials that can turn mechanical force into electricity, and electricity back into mechanical movement. That's the world of piezoelectric and ferroelectric materials, and it's a wild one. These are the kinds of materials that live in sensors, microphones, quartz watches, sonar systems, even medical ultrasound devices. And it all comes down to how their crystal structures behave under stress or an electric field. We'll start with piezoelectric materials. These are materials that generate an electric charge when mechanical stress is applied. The effect works in reverse, too. If you apply an electric field, the material physically deforms, creating a mechanical strain. This two-way street is called the direct and converse piezoelectric effect. The underlying mechanism is surprisingly elegant. In most crystals, when you apply mechanical stress, the positive and negative charge centers still line up. Nothing dramatic happens electrically. But in piezoelectric materials, the crystal lacks a center of symmetry. That means when you apply a force, the internal charge distribution becomes unbalanced. The result, a separation of charges, and that means a voltage shows up across the material. Some of the most commonly used piezoelectric materials include quartz beryllium titanate and lead zirconate titanate. The last one is better known as PZT, and it's a workhorse in practical devices. These materials have specific orientations in which they generate voltage when pressed or bent, and that's something engineers exploit when designing sensors or actuators. The beauty of piezoelectricity is in its simplicity. For example, a quartz crystal in a watch vibrates at a super steady frequency when voltage is applied. Those mechanical vibrations create precise electrical signals that keep time accurately. Flip the use case, press the material instead, and now you have a pressure sensor that turns vibrations or force into measurable voltage. Think of the little mic in your phone or the pickup in an electric guitar. That's piezoelectricity at work. Now, if we zoom in on the atomic level, the piezoelectric effect is all about what happens to dipoles inside the crystal. When you stress the crystal, the internal dipoles shift. They don't cancel each other out anymore, and you get net polarization. The greater the stress, the more dipoles shift, and the larger the electric field that gets created. Let's talk numbers for a second. Not formulas, but behavior. The strength of the piezoelectric response is typically described by a coefficient called the piezoelectric constant, often represented in equations as a letter like d followed by indices. This constant tells you how much electric displacement you get per unit of mechanical stress. It varies widely between materials and also depends on temperature, purity, and how the crystal is cut and oriented. Now enter ferroelectric materials. These are a special class of piezoelectric materials that have a permanent electric polarization, even without any external electric field. That's the key distinction. All ferroelectrics are piezoelectric, but not all piezoelectrics are ferroelectric. In ferroelectrics, the internal dipoles are spontaneously aligned in certain regions called domains. And here's the exciting part: when you apply an external electric field, you can actually switch the direction of these dipoles. That's called polarization switching, and it's the hallmark of ferroelectric behavior. This makes ferroelectric materials great candidates for memory storage. Why? Because you can write a state by aligning the polarization one way and erase or flip it by reversing the field. Once the field is turned off, the polarization stays, just like magnetic memory, but with electric dipoles. That's the basic idea behind ferroelectric RAM, a type of non-volatile memory that keeps data even when the power is off. A typical ferroelectric material is barium titanate. In its high-temperature phase, it has a cubic structure and behaves like a regular dielectric. But as it cools below a certain Curie temperature, its structure distorts into a tetragonal shape, and spontaneous polarization kicks in. You end up with multiple domains, each having dipoles aligned in different directions. These domains can be manipulated by electric fields, pressure, or even light in some cases. Ferroelectricity also leads to a phenomenon called hysteresis. When you plot polarization versus electric field, you get a loop, not a straight line. This loop shows that the material retains some polarization even when the external field is removed. It takes a reverse field to bring the polarization back to zero. This hysteresis loop is a signature of memory and non-linearity in ferroelectric materials. One more cool thing: ferroelectrics are tunable. Their dielectric constant can change dramatically with applied field or temperature. This makes them incredibly useful for tunable capacitors, phase shifters, and frequency-agile devices in communication systems. And we can't skip the mechanical side. Just like in piezoelectrics, ferroelectrics deform under electric fields. But the deformation is often larger and more complex because of domain wall motion. That's why ferroelectric ceramics are used in actuators that need large, precise movements at the micro scale, like in inkjet printers or precision positioning systems. Temperature plays a major role in both piezoelectric and ferroelectric behavior. For piezoelectrics, performance tends to degrade as you approach the Curie temperature. For ferroelectrics, crossing that temperature actually destroys the spontaneous polarization, turning the material back into a simple dielectric. This reversible transition is used in thermal sensors and smart materials that respond differently across temperature ranges. From a practical perspective, these materials are all about energy conversion. Whether it's sensing, actuation, signal generation, or data storage, piezoelectrics and ferroelectrics are the bridge between mechanical motion and electrical signal. Engineers use them wherever compact, efficient transducers are needed. To sum it all up, piezoelectric materials generate voltage from mechanical stress and deform when you apply voltage. Ferroelectric materials take that further, offering permanent polarization and reversible switching, with hysteresis and memory-like behavior. They both rely on non-centrosymmetric crystal structures, internal dipoles, and domain physics to do their magic, and their impact on modern tech is massive. Nanostructures, quantum dots, wires, wells, let's zoom in, and I mean really zoom in, to the nanoscale world, where matter behaves in ways that would seem almost alien if you were only familiar with bulk materials. Welcome to the fascinating territory of nanostructures, specifically quantum dots, quantum wires, and quantum wells. These aren't just tiny pieces of material. They're structures so small that quantum mechanics becomes the dominant force shaping how electrons move and how energy behaves. To understand nanostructures, we need to first grasp a fundamental idea. When you shrink a material down to the nanometer scale, that's a billionth of a meter, electrons inside it can no longer move freely in all directions. Their movement gets restricted or confined, and that changes everything. These confinement effects are what create quantum dots, wires, and wells. They're all built from the same principle: restrict the motion of charge carriers like electrons or holes in one, two, or all three spatial dimensions. Let's start with quantum wells. Imagine a very thin layer of one semiconductor material sandwiched between two layers of another material with a wider band gap. For example, gallium arsenide between layers of aluminum gallium arsenide. The electron is free to move in two dimensions, along the length and width of the layer, but it's tightly confined in the thickness direction. That's a quantum well. Because of that confinement, the energy levels that electrons can occupy become quantized. That means they can only take on specific discrete values, not a continuous range. It's like converting a smooth ramp into a staircase. This gives quantum wells very precise optical and electronic properties. For instance, they absorb and emit light at specific wavelengths, which is why they're used in laser diodes, infrared detectors, and high-efficiency solar cells. Now take that a step further and confine the electrons in two dimensions instead of just one. That's a quantum wire. Here, electrons are only free to move along a single line, one dimension. The cross section of the wire is on the nanometer scale, so the other two directions are so tightly confined that quantum effects dominate there too. Quantum wires have even sharper energy levels than quantum wells and can support exotic effects like quantized conductance, where current flows in discrete steps rather than smoothly increasing. They're being explored for future transistors and nanoscale interconnects in electronic circuits. Finally, if we go all the way and confine the electron in all three dimensions, we get a quantum dot. This is the quantum version of a particle in a box. The electron is trapped. It can't move freely in any direction. Because of that, quantum dots act like artificial atoms. They have discrete, atom-like energy levels. The cool thing is, by changing the size of the dot, you can change the energy gap. Smaller dots have higher energy transitions and emit bluer light. Larger dots emit redder light. This tunability makes quantum dots incredibly useful in things like quantum dot TVs, medical imaging, and next-generation LEDs. At the core of all this is a concept called quantum confinement. When the size of the structure becomes comparable to or smaller than the de Broglie wavelength of the electron, the wave-like nature of the electron becomes dominant. This leads to energy quantization. Electrons can only occupy certain standing wave patterns inside the structure, just like how a guitar string can only vibrate at specific resonant frequencies. Let's say we have an electron in a quantum dot. The simplest model to describe this is the particle in a box problem from quantum mechanics. The energy levels are inversely proportional to the square of the box size. That means, as the dot gets smaller, the energy difference between levels increases. This is why smaller quantum dots glow in the blue and larger ones glow in the red. It's not a coloring dye, it's actual quantum behavior. Now, these nanostructures don't just occur naturally. They're engineered using sophisticated fabrication techniques like molecular beam epitaxy, chemical vapor deposition, or colloidal synthesis. For example, colloidal quantum dots are synthesized in a liquid solution with precise control over their size and surface chemistry. That's why they're already being integrated into display technology, improving color purity and energy efficiency. Quantum wires, on the other hand, are often created using lithographic techniques, where a substrate is patterned and etched to produce nanoscale channels. In advanced setups, self-assembly methods are also used, where the material naturally grows into wire, like shapes under specific conditions. One amazing thing about nanostructures is their potential in quantum computing. Quantum dots are being studied as qubits, the basic units of quantum information, because their discrete energy states can represent the binary 0 and 1, and even combinations of both, thanks to quantum superposition. Plus, their small size and optical responsiveness make them easier to manipulate and integrate into devices. And here's a fun fact: the biological imaging world loves quantum dots. Traditional fluorescent dyes can fade quickly and aren't always easy to tune for different colors. But quantum dots, they're bright, stable, and their emission wavelength depends only on their size. You want a glowing red tag for a protein? Use a 5 nanometer dot. Need green? Go slightly smaller. That level of control is game changing in medical diagnostics and cellular imaging. Despite all their promise, nanostructures also come with challenges. Surface defects can trap electrons or holes, leading to unwanted recombination. That's why surface passivation, essentially coating the dots with protective shells, is essential for stable performance, and manufacturing them at scale with atomic-level precision remains an ongoing research frontier. In terms of applications, we're already seeing quantum wells in commercial lasers, quantum dots in TVs and biolabels, and quantum wires in prototype nanoelectronics. But the full potential is still unfolding, especially as researchers find ways to combine these structures into hybrid devices that offer the best of all dimensions. To wrap this up, nanostructures like quantum wells, wires, and dots represent the frontier of materials engineering. By controlling matter at the scale where quantum effects dominate, we get a whole new toolkit of optical, electrical, and magnetic properties that bulk materials simply can't offer. They're small, but their impact on technology is anything but. Topological insulators and quantum Hall effect. Let's enter the strange but fascinating world of topological insulators and the quantum Hall effect, where electricity flows along edges like it's riding on invisible rails, and insulating materials suddenly start behaving like perfect conductors, but only at their boundaries. This is solid physics meeting high-level quantum mechanics, and it's got that perfect blend of bizarre behavior and cutting-edge potential. We'll start with topological insulators. At first glance, these materials might look like regular insulators. Their bulk, the inside, doesn't conduct electricity. No free electrons to move around, no traditional current flow. But the surface, that's where the magic happens. On the outer edges or surfaces, these materials conduct electricity with incredible efficiency, almost like a metal. And the reason this happens isn't due to impurities or some clever material tweak. It's rooted in the material's topology. Now, topology is a branch of mathematics that studies properties of objects that don't change even when you stretch or bend them. Think of how a donut and a coffee mug with a handle are considered topologically the same. They each have one hole. In the context of materials, this abstract math turns into something very real. The electronic band structure of a topological insulator has features that are topologically protected, meaning they can't just disappear due to defects or noise. The result: these surface states are incredibly robust, resistant to scattering, disorder, and imperfections. What makes this even wilder is spin momentum locking. In topological insulators, the direction an electron moves is tied to its spin. If it's moving one way, it has to spin up. Reverse direction, it must spin down. This means electrons traveling on the surface can't easily reverse course, because doing so would require flipping their spin, which is highly unlikely without magnetic disturbance. This prevents backscattering, a major cause of electrical resistance in traditional conductors. So what's the real-world use of this? For one, these properties make topological insulators incredibly attractive for low-power electronics, spintronics, and even quantum computing, especially when combined with superconductors to potentially form exotic particles like Majorana fermions, which could one day act as fault-tolerant qubits. Now let's shift to the quantum Hall effect, which is another quantum phenomenon that reveals what happens when electrons are squeezed into two dimensions and subjected to strong magnetic fields. Picture a very thin sheet of conducting material, like a two-dimensional electron gas trapped at the interface of two semiconductors. Now apply a perpendicular magnetic field. Electrons begin to move in tight orbits called cyclotron motion, and instead of drifting in a straight path, they follow curved trajectories. In classical physics, you'd expect resistance to increase with magnetic field. But what happens in the quantum world is something entirely different. When the conditions are just right, ultra-cold temperatures and strong magnetic fields, the Hall resistance doesn't vary smoothly. Instead, it becomes quantized, meaning it jumps in perfectly flat steps. This is the quantum Hall effect. The Hall resistance becomes equal to Planck's constant divided by the square of the electron charge, multiplied by 1 divided by n, where n is an integer. That is, Hall resistance equals Planck's constant divided by the square of the electron charge, all multiplied by 1 over n. This isn't a rough approximation. It's an exact relationship. That level of precision is actually the reason why the quantum Hall effect is used today as the international standard for electrical resistance. But there's another twist, the fractional quantum Hall effect. At even lower temperatures and higher magnetic fields, researchers noticed the Hall resistance started quantizing at fractional values, like 1/3 or 2/5. This couldn't be explained by the behavior of single electrons. It turns out that under these conditions, electrons interact so strongly they form a completely new state of matter. It behaves as if the electrons themselves have broken up into smaller pieces, what we call quasiparticles, with fractional charge. This is mind-blowing stuff, and it opens doors to understanding correlated quantum states and potentially even building blocks for topological quantum computers. So how are these two, topological insulators and the quantum Hall effect, connected? The link is in their edge states. In both cases, current doesn't flow through the middle of the material. Instead, it zips along the edges, and it does so without resistance. But while the quantum Hall effect requires a magnetic field to create this behavior, topological insulators can do it without one, thanks to their internal band structure and spin-orbit coupling. This led to the discovery of the quantum spin Hall effect, a time-reversal symmetric version of the quantum Hall effect, but without an external magnetic field. In this case, spin-up electrons travel along one edge in one direction, and spin-down electrons travel in the opposite direction. Again, no backscattering. Just clean, efficient current flow, perfect for next-gen electronics. Topological insulators are being actively explored in materials like bismuth selenide, mercury telluride, and certain transition metal dechalcogenides. In labs, we can fabricate thin films, sandwich layers, and tweak their properties using gate voltages to observe edge conduction and topological behavior. It's also worth noting that three-dimensional topological insulators have surface conduction on all outer layers, not just one edge. This leads to interesting effects when shaped into wires or interfaced with superconductors, where unusual quantum states emerge at the boundary between different materials. From a practical standpoint, the robustness of edge conduction in both quantum Hall systems and topological insulators makes them strong candidates for low-dissipation electronics, fault-tolerant quantum computing, and even new materials for spin-based devices. In short, topological insulators and the quantum Hall effect represent a shift in how we understand conductivity. Instead of asking how electrons move in the bulk, we now ask what happens on the edges, and how topological protections can keep that current flowing even when everything else is working against it. It's solid physics with a quantum twist, and it's reshaping how we think about materials at the fundamental level. Applications in modern electronics and devices. Now that we've explored the theory, structure, and mind-bending quantum effects in solid physics, let's bring it all together and ask, how does this stuff show up in our real-world tech? Because while it's fun to imagine electrons surfing edge states or whispering through superconductors, the real power of solid physics is how it fuels the devices we use every day, often without us even realizing it. Let's start with semiconductors, the cornerstone of modern electronics. Whether you're scrolling on your phone, using a laptop, or watching this video, there's a silicon-based chip at the heart of it. These chips rely heavily on the solid physics principles we've covered: intrinsic and extrinsic semiconductors, doping, band theory, and the behavior of p-n junctions. All of it combines into one beautifully engineered system, allowing logic gates to switch, store, and process information. Transistors are where this becomes physical. A transistor, whether it's bipolar or field effect, uses doped regions and junctions to control the flow of electrons. That's solid physics applied directly to amplification and digital logic. Billions of these transistors make up the central processing units, CPUs, and graphic processing units, GPUs, in computers, phones, and game consoles. Then there's LEDs and laser diodes. These devices rely on direct band gap semiconductors, where electrons drop from the conduction band to the valence band and emit a photon in the process. That's how we get the light in LED screens, laser pointers, optical drives, and even in LiDAR sensors for autonomous vehicles. Let's not forget solar cells. These are also built using p-n junctions, but in reverse. Instead of applying a voltage to get current, they absorb photons to release electrons and generate electricity. This photovoltaic effect is a direct application of solid physics, from understanding band gaps to engineering layers that maximize light absorption and minimize electron-hole recombination. Magnetic storage is another area. Hard drives use ferromagnetic materials to store data. When you write a file, tiny magnetic domains get flipped to align in specific directions, representing binary ones and zeros. Advances in understanding magnetic hysteresis, coercivity, and magnetoresistance have led to denser, faster, and more reliable storage. Flash memory used in SSDs and USB drives depends on insulating layers and trapped charges. That's tunneling, dielectric behavior, and energy states at play. Again, solid physics is behind the scenes making it work. Now enter the world of quantum materials, superconductors, topological insulators, and graphene. These materials are leading us into new frontiers. Superconductors are used in MRI machines, maglev trains, and particle accelerators because of their zero resistance current flow and strong magnetic field interactions. Research is ongoing to bring this to power grids and ultra-efficient electronics. Topological insulators and quantum Hall systems, which we covered earlier, are being investigated for fault-tolerant quantum computing. Their edge states and spin, momentum locking could be the key to stable, scalable qubits. Graphene and other 2D materials are being explored for flexible electronics, ultra-fast transistors, and even transparent touchscreens. Their electronic, thermal, and mechanical properties open up entire new categories of devices. Sensors are also a huge area where solid physics finds daily application. Hall effect sensors detect magnetic fields, useful in automotive systems, smartphones, and industrial controls. Piezoelectric materials detect pressure and convert it into electrical signals, used in microphones, medical ultrasound, and wearable tech. Even in displays, you'll find solid physics at work. Liquid crystal displays LCDs, organic LEDs, OLEDs, and quantum dot displays all rely on controlled electron behavior, energy states, and photon emission principles. As we move toward quantum computing, spintronics, and neuromorphic systems, solid physics continues to be the backbone of innovation. Devices are shrinking, becoming more energy efficient, and more reliant on novel materials that exhibit quantum effects at room temperature or under specialized conditions. And then there's optoelectronics, a fusion of optics and electronics. Think fiber optic communication, photodetectors in cameras, and IR sensors in facial recognition. These devices all depend on precise control of electron-photon interactions guided by principles of solid physics. So in summary, the ideas you've learned throughout this video: band gaps, electron mobility, spin alignment, carrier concentration, aren't just academic. They're powering the future. They're baked into the chips in your devices, the screens you stare at, the cars you drive, the medicine you receive, and the infrastructure we're building for the next generation. Solid physics is the language of modern electronics. And now you speak it.